The story of life does not begin on Earth. It begins in the silence of the void, in the searing light of the first dawn when the universe itself came into being. Some 13.8 billion years ago, every atom that would ever breathe, dream, or wonder was compressed into a single point of energy and potential. The Big Bang was not an explosion in space, but an explosion of space. The birth of time, matter, and law. In less than a second, temperature and density reached unimaginable magnitudes, and the first rules of physics froze into being. Gravity, electromagnetism, and the nuclear forces formed the scaffolding upon which all later structure would arise. Out of the chaos, order began to whisper its first words. For hundreds of thousands of years, the universe was opaque, a radiant soup of particles, electrons and protons bound by energy, but not yet by structure. Then came a great cooling, a cosmic recombination, when temperature dropped enough for the first atoms to form. Hydrogen and helium, the simplest elements, condensed from the plasma, allowing light to travel freely for the first time. That light, stretched and reddened across eons, is the cosmic microwave background that still bathes every corner of the sky. It is the fossil glow of our origin, the after-image of creation itself. Gravity, the sculptor of all complexity, began its work in that transparent universe. Regions slightly denser than their surroundings drew in matter, forming the first halos, the dark gravitational wells in which galaxies would be born. As the eons unfolded, these halos condensed into vast rotating systems, where hydrogen fell inward and ignited under its own weight. The first stars flared into existence perhaps 100 million years after the beginning. Beacons in a universe of darkness. They lived fast and died young, their immense cores forging heavier elements through nuclear fusion: carbon, nitrogen, oxygen, silicon, and iron. The alphabet of future biology. When these early giants perished in supernovae, they scattered their enriched material through the cosmos, seeding the clouds that would give rise to second and third generation stars. It was through this process of stellar death that the universe learned to write the language of life. Each generation of stars added its verse to the cosmic song. Nebulae became laboratories of chemistry, where atoms combined into molecules in the cold dark between stars. Here, in the infrared glow of molecular clouds, carbon joined oxygen to form carbon monoxide. Nitrogen and hydrogen bonded to create ammonia. Icy grains condensed with simple organics like methanol and formaldehyde. The seeds of amino acids and sugars, the molecular precursors of biology, took shape long before any planet existed. In this sense, life's chemistry was not Earth's invention, but the universe's inheritance. When our solar system formed 4.6 billion years ago, it did so within one of these enriched molecular clouds, a rotating disk of gas and dust that had been through many cycles of stellar birth and death. Within its collapsing heart, the sun ignited, and around it a flattened protoplanetary disk began to coalesce into worlds. The material that would become Earth contained atoms once buried in ancient stars, atoms that had traveled across interstellar gulfs for billions of years. Every human being carries within their bones and blood a direct lineage to that stellar ancestry. The calcium in our teeth was born in the heart of a red giant. The iron in our blood, in a dying supernova. Carl Sagan's poetic truth, that we are made of stardust, is not metaphor, but physics. Once planets solidified and cooled, chemistry awakened anew. On Earth, the interplay of sunlight, atmosphere, and ocean began to weave more intricate patterns of reaction. The boundary between geology and biology blurred as minerals catalyzed the formation of organic molecules. The ancient Earth was not a tranquil world, but a cauldron of energy. Lightning flashing across methane skies, volcanic vents pouring minerals into primordial seas, ultraviolet radiation raining upon the surface. In such crucibles, carbon chains grew, folded and recombined, forming the prototypes of the molecules that would one day encode heredity. Somewhere in that world of chaos and potential, the line between the inanimate and the animate was crossed. Yet the emergence of life cannot be told as a simple sequence of accidents. It reflects the deep capacity of matter to organize itself under the influence of energy and law. From the condensation of hydrogen to the replication of DNA, the same physical principles operate. Systems far from equilibrium use the flow of energy to build complexity. Life, in this view, is not a freak event, but a natural expression of the universe's drive toward structure. An extension of the same processes that built stars and galaxies. It is order sustained by energy, encoded in chemistry, and sculpted by time. The cosmic story of matter and life is thus one continuous arc of increasing intricacy. Hydrogen became helium, helium became carbon, carbon became protein, and protein learned to think. From the first nuclei to the first neuron, a single thread of evolution winds through cosmic history. At each scale, new forms of organization arise. Subatomic forces yield atoms, atoms yield molecules, molecules yield cells, and cells yield consciousness. There is no absolute boundary separating these domains, only thresholds where complexity crosses a new frontier. The emergence of life also transformed the planet itself into a dynamic, self-regulating entity. Through photosynthesis, respiration, and carbon cycling, living organisms reshaped the atmosphere and climate, stabilizing conditions for their own continuation. This feedback between biology and environment exemplifies what James Lovelock would later call Gaia, the planet as a single physiological system. But long before humanity could name it, Earth was already a self-aware experiment in cosmic chemistry, a world that had learned to feel its own processes. If the universe is indeed alive in its capacity to generate life, then consciousness is its means of seeing itself. Every sentient being becomes a node of awareness, through which the cosmos contemplates its own origins. This idea, poetic yet grounded in science, forms the philosophical backbone of astrobiology. That life and mind are not mere ephemera, but emergent properties of matter in motion. We are the cosmos observing itself through the lens of biology and reason. The narrative of cosmic genesis is still unfolding. Our telescopes now peer into the faint light of galaxies billions of years old, revealing how common planets are and how universal chemistry seems to be. Spacecraft wander the solar system in search of biosignatures, while astronomers detect atmospheres around distant worlds and analyze their spectra for traces of oxygen or methane. In laboratories, chemists coax simple molecules into self-assembly, and biologists probe the boundaries of what it means to be alive. Every discovery adds another stanza to the universal story. The ancient philosophers imagined a living cosmos, a universe suffused with spirit or anima mundi. Today, science revives that intuition in a different language. The cosmos may not be conscious in the human sense, yet it produces consciousness as naturally as it produces light. From the first flicker of hydrogen fusion to the spark of thought in a human brain, the continuum of transformation remains unbroken. Life, then, is not an anomaly, but the flowering of cosmic order, the song of atoms that have learned to sing. And so the story of matter and life is a single seamless narrative. Energy becoming form, form becoming awareness. The same forces that shaped galaxies also shape our cells, The same chemistry that filled interstellar space now flows in our veins. When we look up at the stars, we are not gazing into something foreign, but into our own beginning. The cradle of every heartbeat, every question, every dream. The universe is not merely the stage on which life has appeared. It is the author, the setting, and the evolving story itself. Chemical evolution in a 13.8 billion-year-old universe. The universe began as a singular simplicity, a seething field of pure energy and fundamental particles, yet hidden within that apparent austerity was the potential for every molecule, mineral, and organism that would ever exist. When the newborn cosmos cooled during its first 3 minutes, it performed the earliest act of chemical creation, the fusion of protons and neutrons into the light nuclei of hydrogen, helium, and traces of lithium. This process, known as Big Bang nucleosynthesis, set the elemental inventory for hundreds of millions of years to come. The universe emerged chemically poor but pregnant with possibility. 92% hydrogen, 8% helium, and a whisper of everything else. For 500 million years, the cosmos darkened into a long, austere adolescence. Gravity gathered matter into filaments and knots, while radiation streamed through expanding space. Chemistry at this epoch was confined to the simplest bonds. The occasional molecule of hydrogen, H2, deuterium hydride, or helium hydride ion. The first molecule ever to exist. These primitive species, forming in rarefied gas, controlled the rate at which clouds could cool, allowing them to collapse further under gravity. Without molecular hydrogen's ability to radiate away heat, the first stars might never have ignited. Thus, even in the thin chemistry of that early era, the seeds of complexity were already doing their quiet work. When the first stars lit, chemical evolution accelerated dramatically. Stellar furnaces became cosmic laboratories, forcing nuclei together under immense pressure. Hydrogen fused into helium, helium into carbon and oxygen, and through successive reactions up to iron, the terminal element of exothermic fusion. Each star lived as an alchemist, transmuting simplicity into diversity. And when its life ended in a supernova, those new elements were hurled back into space. In their incandescent deaths, stars enriched their surroundings with carbon for organic backbones, oxygen for water, silicon for rocks, and iron for the magnetic hearts of future planets. Every explosion wrote new symbols onto the periodic table of the universe. Across billions of years and billions of stellar generations, the galactic medium thickened with dust, molecules, and heavy elements, what astronomers call metallicity. The earliest galaxies were chemically barren, but by the time our Sun formed, the Milky Way had been seasoned by countless stellar lives. Each new cycle of birth and destruction raised the metallicity a little higher, widening the menu of possible compounds. The cosmos learned chemistry by iteration. Every supernova was a lesson, every nova a revision, every planetary nebula an experiment in molecular sculpture. Out of that slow apprenticeship came the raw ingredients for life. In the cold wombs of interstellar clouds, chemistry took on new subtleties. Dust grains, tiny silicate and carbon particles, served as catalytic surfaces where atoms could meet and bond. Hydrogen, carbon, oxygen, and nitrogen assembled into simple organics, shielded from harsh ultraviolet radiation by the very dust that nurtured them. Observations of these clouds reveal a surprising richness. Formaldehyde, methanol, formic acid, and even amino acid precursors drift among the stars. Radio telescopes have detected over 200 distinct molecular species in space, including complex organics such as polycyclic aromatic hydrocarbons, which may account for much of the Milky Way's faint infrared glow. Long before planets coalesced, the universe was already experimenting with biochemistry. Chemical evolution is therefore not confined to the laboratory of Earth, but is a cosmic process woven through time. The same rules of quantum mechanics and thermodynamics that shape reactions in a test tube apply equally to nebulae and comets. Bond strengths, activation energies, and molecular geometries do not depend on location. This universality implies that wherever suitable conditions arise, moderate temperatures, abundant carbon, a solvent or surface to mediate reactions, chemistry will explore the same pathways toward complexity. Life's emergence, then, is not a miracle of chance, but the outcome of nature's persistent tendency to build upon itself. As galaxies matured, the interplay between star formation and chemical enrichment produced a layered cosmic ecology. Regions dense in gas became stellar nurseries, exhausting themselves in bursts of starbirth, then resting as supernova. Feedback scattered metals into the interstellar medium. Spiral arms recycled this material over and over, producing gradients in composition. The galactic core metal-rich, the outskirts primitive. Planets forming nearer the center might possess more iron and carbon. Those in the halo, fewer volatile compounds. Thus, even at the galactic scale, chemistry dictates destiny. Our solar system emerged from one of these recycled clouds about 4.6 billion years ago. Spectroscopy of the Sun shows that it is a third-generation star, its composition already flavored by the ashes of many predecessors. Within the protoplanetary disk surrounding the infant Sun, temperature fell with distance, determining which compounds could condense. Close in, refractory minerals like olivine and iron solidified. Farther out, ices of water, methane, and ammonia froze onto grains. These gradients sculpted the architecture of the solar system. Rocky inner planets, gas giant outer worlds, and an icy frontier beyond Neptune. Chemistry, governed by temperature and pressure, decided the fates of worlds. In this same disk, microscopic solids began to stick together through electrostatic attraction, growing into planetesimals, the embryos of planets. Within them, radioactive heating and impacts created miniature crucibles where further reactions occurred. Carbonaceous chondrite meteorites, relics of these early bodies, still bear a record of that epoch. Amino acids, carboxylic acids, and nucleobase analogues preserved in stone for billions of years. These findings blur the line between astrophysics and biology. The ingredients of life were not confined to one lucky planet. They were disseminated widely across the young solar system, possibly across interstellar space. Chemical evolution continued on planetary surfaces. Once Earth cooled and oceans condensed, water became the great solvent that unlocked new possibilities. Dissolved minerals, atmospheric gases, and energy from sunlight or lightning drove networks of reactions that produced ever more complex molecules. In the deep sea, hydrothermal vents provided a steady supply of heat and catalysts, precipitating iron-sulfur compounds that may have mediated the formation of metabolic pathways. The leap from chemistry to biology, from geochemistry to biochemistry, may have been gradual, a continuum of self-organizing systems exploring the thermodynamic landscape until one achieved replication. Whether by chance or by inevitability, chemistry had crossed a threshold. Matter had learned to copy itself. Viewed from the cosmic perspective, chemical evolution is an unbroken sequence, linking the first atoms to the first cells. Hydrogen fusion built the periodic table. Supernovae scattered it. Planetary chemistry refined it. And biology exploited it. Each step emerged from the interplay between energy flow and the tendency of matter to organize when far from equilibrium. Even today, the process continues. New stars are forming in Orion's nebula, their disks alive with chemical activity. In those swirling clouds lie the raw materials for future oceans, atmospheres, and perhaps even civilizations that will one day trace their ancestry, as we do, to the same universal chemistry. Modern astronomy allows us to witness this grand narrative in real time. Spectrometers aboard space telescopes dissect starlight to reveal chemical fingerprints billions of light years away. We can now map the enrichment history of galaxies, measuring how metallicity rises with age, how dust recycles through supernova remnants, and how molecular gas fuels the next wave of star formation. In this data, we glimpse a living cosmos, one that breathes in cycles of creation and dissolution. To study chemistry on such scales is to realize that the universe itself is a continuous reaction vessel, vast beyond comprehension, yet governed by the same equations that describe a flask in a chemist's hand. As we trace this evolution over 13.8 billion years, a pattern becomes clear. The cosmos begins simple and becomes complex, not through design, but through the self-propagating consequences of physical law. Each layer of structure opens new chemical degrees of freedom. Atoms make molecules, molecules make minerals, minerals make membranes, membranes make metabolism. The chain of being is not mystical but molecular, yet its implications are profound. Life, rather than a local curiosity, may be the natural culmination of universal chemistry striving toward greater organization. In the end, chemical evolution is the quiet architect behind everything we see, the invisible hand that turns energy into form. From the fusion cores of ancient stars to the biochemical engines within our cells, the same dance of electrons governs all transformations. The periodic table is our genealogy, each element a chapter in the universe's autobiography. To read it is to recognize that we are not spectators, but participants in a 13.8 billion-year experiment still unfolding. A cosmic chemistry set whose latest product is the human mind pondering its own origins. The elements of biology, forged in stars. Every living thing, every cell and heartbeat, every leaf and lung is a recitation of an older language, the elemental grammar of the stars. The breath of life is written not in mystic ink, but in the ashes of suns. The residue of fusion and explosion scattered through the Milky Way. The elements that define biology, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, were not present at the dawn of time. They were manufactured in furnaces so vast that the energy released in a single heartbeat of their existence could outshine a galaxy. The story of these elements is the story of cosmic memory. The universe learning to build the structures through which it could one day know itself. Hydrogen, the most ancient of atoms, emerged directly from the Big Bang, the firstborn child of creation. In its nucleus of a single proton lies simplicity incarnate, and yet hydrogen is the root of all diversity. When drawn into the gravity wells of stars, it becomes the fuel for transformation. Inside stellar cores, hydrogen nuclei collide at speeds of thousands of kilometers per second, fusing to form helium and releasing photons that take millions of years to escape to the surface. Each such reaction converts a fraction of mass into energy, sustaining the light of the cosmos. Through hydrogen, the universe not only illuminates itself, but begins the long chemical ascent toward complexity. Helium, the second product of cosmic alchemy, represents the first fusion victory over simplicity. In it lies the potential for heavier elements, for carbon and oxygen, and the chain of atoms essential to life. But the synthesis of these heavier nuclei demanded environments even more extreme. Stars larger and hotter than our sun. Within their blazing interiors, when the hydrogen fuel ran low, gravity compressed the core until temperatures climbed to hundreds of millions of degrees. Under those conditions, 3 helium nuclei could combine in a delicate sequence known as the triple alpha process, creating carbon, the backbone of life's molecular architecture. Carbon's birth is a miracle of resonance. For 3 helium atoms to unite, an intermediate beryllium-8 nucleus must form and survive just long enough to capture another helium. The odds are infinitesimal, but nature found a narrow window of possibility. In the 1950s, astrophysicist Fred Hoyle predicted that for this reaction to occur efficiently, carbon must possess an excited nuclear energy level, a resonance. At exactly 7.65 million electron volts. When experiment confirmed this state, Hoyle remarked that the universe seemed a put-up job. Whether coincidence or cosmic necessity, that resonance ensured the abundance of carbon throughout the cosmos. Without it, stars would die sterile, and no carbon-based life could exist. The coincidence lies at the heart of the anthropic enigma, the sense that physical constants are tuned just finely enough for the universe to become aware of itself. Once carbon formed, the way was open to oxygen. In the fusion pathways of massive stars, carbon captured helium nuclei in successive steps, building neon, magnesium, and oxygen. Each of these nuclei, stable and robust, would play a vital role in the later chemistry of planets. Oxygen, with its twin hunger for electrons, became the architect of water and the master of metabolism. Combined with hydrogen, it created the universal solvent in which biological reactions could flourish. Combined with carbon, it built the volatile gases of atmospheres and the long chains of sugars that feed life. The balance between carbon's bonding versatility and oxygen's chemical appetite forms the axis around which biology spins. Nitrogen, too, was forged in stellar hearts, though by more circuitous routes. During the carbon-nitrogen-oxygen cycle, an alternative fusion process in massive stars, nitrogen accumulates as an intermediate product. When those stars die, nitrogen joins the interstellar medium, where it becomes a crucial component of amino acids and nucleobases. In life's lexicon, nitrogen grants flexibility. It bridges carbon chains, builds proteins, and encodes genetic information. Its cosmic origin is thus a quiet counterpart to the fiery births of carbon and oxygen. Less dramatic, but equally indispensable. Phosphorus and sulfur, though rarer, are equally vital. Phosphorus arises in the final stages of stellar evolution, during supernova nucleosynthesis when shock waves compress the outer layers of massive stars. Its unique ability to form high-energy bonds makes it the cornerstone of adenosine triphosphate, the molecule that powers every living cell. Without phosphorus, energy could not be stored and transferred in biological systems. Sulfur, formed in similar cataclysms, gives proteins their structure through disulfide bonds and plays a role in the metabolism of primitive organisms. Together, these elements complete the biochemical sextet, CHONPS, from which all known life is built. When a massive star's nuclear fuel is exhausted, fusion ceases to generate enough pressure to resist gravity. The core collapses in milliseconds, reaching densities that force protons and electrons to merge into neutrons. The outer layers rebound and explode outward as a supernova, ejecting billions of tons of enriched material into space. For a brief moment, the star shines as brightly as an entire galaxy, and in that incandescent breath, new elements are forged: copper, zinc, silver, gold, uranium. Each explosion seeds the cosmos with heavy atoms that will become the ores of future worlds and the catalysts of future life. Every atom of iron in our blood, every trace of calcium in our bones, passed through such an inferno. Supernovae, however, are only one mechanism of enrichment. In the later lives of sun-like stars, when hydrogen and helium burning produce a buildup of carbon and oxygen, pulsations eject outer layers into space as gentle winds. These asymptotic giant branch stars create dust grains rich in silicates and graphite. In the cold between stars, these grains act as the raw material of molecular clouds, providing the surfaces on which new chemistry can flourish. Thus, through both violence and gentleness, the universe circulates its elemental wealth. Destruction and creation entwined in a continuous cycle of renewal. By the time the Sun was born, roughly 9 billion years after the Big Bang, the interstellar medium had been enriched to a metallicity sufficient for complex chemistry. The protoplanetary disk that surrounded our young star was thick with heavy elements, ices and dust, the inheritance of generations of stellar deaths. It was within this chemically fertile environment that Earth formed, gathering its crust, oceans, and atmosphere from the debris of earlier worlds. The oxygen that would later fill those oceans was already ancient. The carbon that would knit into the first cells was as old as the galaxy itself. The atoms of life were not conjured anew. They were merely recombined into a novel architecture. To trace life's elements to their stellar origins is to perceive continuity rather than separation. There is no metaphysical divide between astrophysics and biology. They are chapters of the same narrative, written in different alphabets of matter. The periodic table becomes a map of evolutionary history, each element a milestone in the universe's unfolding complexity. The lighter elements embody the simplicity of the beginning. The heavier ones embody the creative culmination of countless stellar lives. We are, in the most literal sense, the chemistry of the cosmos arranged into awareness. This understanding transforms the way we view ourselves. Human beings are not foreign intruders in an indifferent universe, but native expressions of its deepest laws. The same nuclear reactions that sustained the first stars now sustain our own biology. Carbon bonds release energy in our mitochondria, as fusion releases energy in the sun. The parallel is profound. Life mirrors the processes that forged it. In each breath, oxygen binds to iron in hemoglobin, just as oxygen once fused with carbon in a star's heart. The continuity between stellar and biological chemistry is complete. The furnace and the cell obey the same principles, differing only in scale and context. When we speak of life as stardust, we are not indulging in poetry, but acknowledging a physical lineage. The calcium that strengthens a bird's egg, the sodium that fires a neuron, the phosphorus that energizes a cell. All are ancient travelers, born in stellar furnaces and refined by time. The human body is thus an archive of the cosmos, a layered record of nucleosynthesis written in flesh. To exist is to remember, not through thought but through matter itself. Astrobiology extends this revelation beyond sentiment into scientific expectation. If the same elements are produced in every galaxy, and if those elements naturally form the same molecular families, then life's potential is universal. The chemistry that gave rise to Earth's biosphere is not a local accident, but a cosmic habit. Wherever stars live and die, they manufacture the ingredients for biology. Wherever planets form, those ingredients fall like cosmic pollen upon their surfaces. The implication is staggering. The universe is predisposed to life because it continually forges the materials that make life possible. Across the Milky Way, newborn stars shine within nebulae enriched by generations of predecessors. In each such nursery, disks of dust and gas condense into planets, inheriting the same elemental palette that once painted our world. Some of those planets will host oceans, atmospheres, and perhaps biospheres. Others will remain barren, their chemistry frozen in equilibrium. But all share a common ancestry, the legacy of stellar nucleosynthesis. The stars are not merely distant suns. They are our ancestors, the cosmic artisans of every cell, every seed, every song. In the end, the elements of biology are more than chemical tools. They are bridges between the inanimate and the living, between the furnace of a dying star and the whisper of a human heartbeat. To follow their journey is to glimpse a universe in which creation never truly ends, where every atom is destined for transformation. The cosmos began as hydrogen, but through time, gravity, and fire, it has become capable of memory and meaning. The stars forged not only the atoms of life, but the minds that can finally understand them. Energy, entropy, and the thermodynamics of life. If the cosmos is the stage upon which matter plays its eternal drama, then energy is the music, invisible, pervasive, transforming all that exists. Every movement of a planet, every flicker of a star, every synaptic spark in a living brain owes its reality to energy's restless circulation. From the first instant of the Big Bang to the beating of a heart, the story of life is inseparable from the story of energy's flow and its ceaseless negotiation with entropy, the measure of disorder, the shadow that follows all creation. In the beginning, energy and matter were one. The early universe was a cauldron of radiation, expanding and cooling as energy transformed into particles. The balance between expansion and gravity set the initial thermodynamic stage. A universe racing toward disorder, yet continually birthing pockets of order. Stars condensed from turbulent clouds, galaxies assembled from collapsing halos, and within those galaxies, planets cooled and solidified. These structures arose not in defiance of entropy, but because of it. Where energy could flow from a hot source to a cold sink, gradients formed, and gradients are the engines of structure. The laws of thermodynamics, humanity's distilled understanding of how energy moves and changes, are as fundamental to life as DNA. The first law tells us that energy cannot be created or destroyed, only transformed. The second law tells us that in every transformation, some energy becomes unavailable for work, dispersing as heat. Entropy, in this context, is not chaos, but balance, the universal tendency of energy to spread. It is the ultimate bookkeeper, ensuring that every act of creation carries a thermodynamic cost. Stars burn hydrogen at immense pressure and temperature, releasing light while increasing the entropy of the cosmos. Life, too, must pay its dues, maintaining local order only by exporting disorder to its surroundings. Yet within that austere framework lies the possibility of complexity. The very existence of entropy creates the conditions for self-organization. Where energy flows persistently through matter, structures can arise to dissipate that energy more efficiently. The universe seems to favor such systems. Vortices in clouds, spiral galaxies, hurricanes, and cells all share the property of being far from equilibrium. They are not static. They are dynamic equilibria, temporary islands of order maintained by the constant throughput of energy. Life is the most exquisite of these systems, a network of molecular reactions designed to capture, store, and redistribute energy in ways that reduce local entropy while amplifying the overall entropy of the environment. The Sun is the source of almost all energy driving Earth's biosphere. Each second it converts nearly 4 million tons of mass into radiant energy, bathing the planets with photons that represent the difference between stellar core temperature and cosmic darkness. Earth, receiving but 1/1000th of that flow, transforms sunlight into chemical bonds through photosynthesis. Green leaves, chlorophyll molecules, and bacterial pigments act as quantum machines, converting the raw flux of photons into the structured sugars that sustain nearly all life. In this process, low-entropy sunlight becomes high-entropy infrared radiation, while the captured fraction feeds metabolism. Thus, the biosphere operates as a grand thermodynamic system, open, adaptive, and driven by disequilibrium. Life's persistence depends on this disequilibrium. The Earth absorbs shortwave energy from the Sun, and emits longer wavelength radiation back into space. The difference in energy quality between incoming and outgoing photons defines a gradient that living organisms exploit. Without it, the planet would settle into uniform equilibrium, a frozen state devoid of chemistry or change. Entropy is not the enemy of life, but its silent ally. For only in a universe tending toward equilibrium can pockets of non-equilibrium exist. As the physicist Erwin Schrödinger famously observed, living organisms feed on negative entropy, importing order from their environment to maintain their internal structure. The thermodynamic logic of life is therefore the logic of flow. A cell is not a thing so much as a process, a membrane-bound whirlpool of energy transformations. Inside it, molecules participate in endless cycles of synthesis and degradation, each reaction coupled to another, so that the waste heat of one becomes the fuel of the next. Adenosine triphosphate, ATP. Molecules act as currency, storing energy in the tension of phosphate bonds and releasing it where work is required. Enzymes lower activation barriers, guiding reactions along precise pathways, while membranes maintain the electrical and chemical gradients that power them. The result is a controlled fall. Energy cascading from high potential to low, building transient order in the descent. From the perspective of physics, every living organism is a heat engine. It draws energy from a source: sunlight, chemical reactions, geothermal vents, performs work and expels waste heat. But unlike man-made engines, life is self-repairing and self-replicating. It is a network of feedback loops that preserves itself against decay. The remarkable thing is not that such systems exist, but that they appear to be statistically favored wherever suitable conditions arise. Chemical networks that can dissipate energy more efficiently tend to proliferate, leading to a natural selection of energy processes. In this sense, evolution is a thermodynamic imperative. The universe experimenting with ever more sophisticated ways to convert energy and export entropy. Consider the example of early microbial mats forming around hydrothermal vents on the ocean floor. Here, the steep temperature and chemical gradients between hot, mineral-rich vent fluids and cold seawater created abundant free energy. Life's earliest metabolisms may have exploited these gradients directly, using iron-sulfur minerals as catalysts. The vent environment mirrors the broader cosmic pattern: energy flowing through matter, driving self-organization. The same principle governs the birth of stars, the formation of storms, and the operation of brains. Wherever gradients exist, complexity follows. As the Earth aged and biological systems diversified, life learned to harness more subtle forms of energy. Photosynthesis tapped into the almost limitless flow of solar radiation, while respiration evolved to extract stored energy from organic molecules. In both cases, electrons, tiny quanta of charge, carry energy across molecular circuits, descending through potential gradients like water down a mountainside. The intricate choreography of these reactions obeys the same thermodynamic principles that govern a collapsing star. Energy seeks the lowest available state, and in doing so, it creates patterns of astonishing beauty. Even consciousness, that crown of biological evolution, obeys these laws. The brain consumes 1/5 of the body's energy, converting chemical potential into electrical activity, generating heat as it thinks. Each synaptic firing, each thought or dream, is an expression of the second law, an exchange between order and entropy, between fleeting structure and inevitable decay. Yet within that transient order arises awareness, meaning, and imagination. The dance between energy and entropy not only sustains life, but gives rise to mind, the ultimate pattern within the pattern. The thermodynamic arrow of time ensures that all systems eventually decay. Stars exhaust their fuel. organisms age and die. Even galaxies will fade as energy gradients even out. On the largest scales, the universe tends toward thermal equilibrium, the so-called heat death, a state of uniform temperature and maximum entropy. But this distant fate does not negate the creativity of the present. The second law, far from being a sentence of doom, is the very reason anything happens at all. Without the flow from order to disorder, there would be no stars, no planets, no life, and no consciousness to contemplate their passing. The inevitability of decay is the price of existence itself. In this light, the universe resembles a vast river of energy cascading down a cosmic slope. Along its course, eddies and whirlpools form, transient, self-organizing structures like galaxies, storms, and living beings. Each eddy endures by channeling the river's flow through itself, shaping the current even as it is shaped by it. Life is such an eddy, a local reversal sustained by the global tide. The second law ensures that the river will never cease to flow, and in that perpetual descent lies the possibility of infinite forms of organization. Human technology, too, is a continuation of this thermodynamic lineage. Our machines, cities, and civilizations are extensions of the same principle. Complex systems that process energy to maintain order. The fire we harnessed in prehistory is the same combustion that powers stars. The circuits in our devices echo the electron flows in living cells. Civilization can thus be seen as the biosphere's next phase of energy management, a planetary-scale metabolism built on the same rules that govern the cosmos. Whether this expansion will stabilize or consume itself depends on how wisely we navigate the flow. Ultimately, life's relationship with energy and entropy is one of profound balance. To live is to exist in a state of poised instability, perpetually falling toward disorder, but continuously reorganizing on the way down. Every heartbeat, every cell division, every thought is a negotiation between decay and persistence. We are not fighting entropy. We are dancing with it. A choreography that began when the first atoms learned to capture light and continues as those atoms contemplate their origins. In that delicate balance between energy and entropy lies the secret of all existence. The universe builds order, not despite disorder, but because of it. Cosmic abundance and the inevitability of chemistry. If one were to step back and gaze upon the universe not as empty space, but as a tapestry of elements, a different picture would emerge. A cosmos brimming with matter, structure, and chemical potential. The night sky, which to the unaided eye appears serene and distant, is in fact a sea of reactions, an endless laboratory where atoms meet, combine, and dissolve in a perpetual ballet of creation and decay. The vastness of space is not a void. It is a crucible of abundance. Everywhere we look, from the coldest interstellar clouds to the hottest stellar cores, chemistry thrives, guided by the same universal laws. And within this profusion, life's ingredients arise as naturally as rain in a storm. The key to this abundance lies in the generosity of the cosmos. Hydrogen and helium, formed in the Big Bang, account for nearly all of the universe's mass. But it is the tiny remainder, the trace elements forged in stars, that provide the palette of complexity. Astronomers often speak of metals, meaning all elements heavier than helium, as the fingerprints of stellar generations. These elements are not scattered sparsely, but distributed widely, diffused through the interstellar medium, incorporated into dust grains, comets, and planets. Each new star forms from recycled matter, inheriting the chemical memory of those that came before. The Milky Way, our galactic home, is thus an ever-renewing organism of matter, continuously birthing, digesting, and redistributing its own components. When spectrometers dissect starlight, they reveal the universe's astonishing uniformity. Across billions of light years, the same atomic signatures repeat, hydrogen's deep crimson lines, oxygen's green glows, carbon's faint ultraviolet bands. This homogeneity is one of the most profound facts in science. It tells us that chemistry is not parochial, but universal, that the same reactions possible on Earth occur equally well in the heart of a nebula or on the surface of an alien world. The cosmos, for all its enormity, obeys one language of matter, a syntax written in quantum mechanics and thermodynamic law. Wherever atoms exist, chemistry follows. Wherever chemistry thrives, the potential for life quietly stirs. Even in the harshest environments, molecules assemble and persist. In interstellar clouds at temperatures barely above absolute zero, dust grains coated in ice become tiny laboratories. Ultraviolet radiation from nearby stars provides just enough energy to break and reform chemical bonds, synthesizing simple organics such as methanol, formaldehyde, and acetaldehyde. Cosmic rays, high-energy particles coursing through space, drive additional reactions, spurring the creation of amino acid precursors and carbon chains. Observations with radio telescopes like ALMA and the Green Bank Observatory have detected more than 200 distinct molecular species in such clouds. Some are complex enough to challenge our notion of inorganic chemistry. In the Orion Nebula, astronomers have found traces of formamide, a compound central to prebiotic synthesis on Earth. In Sagittarius B2, a massive molecular cloud near the galactic center, they have identified ethyl formate, the molecule that gives raspberries their scent. The heavens, it seems, already smell faintly of biology. This ubiquity suggests that chemistry is not an incidental byproduct of physics, but one of its inevitable consequences. The atomic structure of carbon, for instance, virtually guarantees its dominance in molecular diversity. With 4 valence electrons, carbon can bond with up to 4 other atoms, forming chains, rings, and lattices of extraordinary versatility. It is the Lego block of the universe, able to construct both the graphite in meteorites and the enzymes in cells. Silicon, often proposed as a hypothetical alternative, lacks carbon's flexibility, forming brittle bonds that falter in liquid water. Nature, through billions of experiments across galaxies, appears to have settled on carbon as its universal medium of complexity. Hydrogen and oxygen, likewise, are cosmically abundant, forming water, a solvent so adaptable that it dissolves and transports nearly every molecule relevant to metabolism. The periodic table is not a random collection of possibilities. It is a map of inevitable relationships, pointing toward life's chemistry as a natural destination. The notion of inevitability extends to planetary formation itself. Once stars form, disks of gas and dust inevitably swirl around them, condensing into planets, moons, and comets. Each of these bodies carries the chemical signature of its birth cloud. Comets preserve ancient ices rich in organic molecules, while asteroids contain amino acids and nuclear base analogues. When such bodies collide with young planets, they deliver their cargo like cosmic messengers, seeding surfaces with the materials of life. This process, called exogenous delivery, may have been crucial for Earth, providing water and carbon compounds during its violent youth. But it is not unique to our planet. Everywhere planetary systems arise, comets and asteroids form, collide and migrate. The same processes must occur around other stars, ensuring that the chemistry of life is distributed widely, perhaps universally. Modern missions have confirmed this cosmic fertility within our own solar system. The Rosetta spacecraft's analysis of Comet 67P revealed a treasure trove of organic compounds, including amino acid glycine and phosphorus. Essential ingredients for life. The Cassini probe's flybys of Saturn's moon Enceladus detected plumes of water vapor laced with methane and complex hydrocarbons. On Titan, methane rains fill lakes and seas, while ultraviolet light crafts elaborate organic hazes in its orange sky. Even Mars, long considered barren, has yielded evidence of preserved organics in its rocks and soil. The solar system, rather than a sterile set of worlds, is a gallery of chemical creativity, a microcosm of the universe's larger pattern. Underlying this universal chemistry is a profound principle. Once matter exists in abundance, complexity becomes statistically unavoidable. The physicist Ilya Prigogine described this as order through fluctuations. The tendency of systems, far from equilibrium, to generate patterns spontaneously. Whether in a turbulent atmosphere, a galactic spiral, or a biochemical network, randomness and interaction breed organization. Chemistry, in this view, is not a fragile accident, but an expression of the universe's inherent creativity. Given time, energy, and a sufficient diversity of atoms, molecules will not merely form. They will evolve toward greater intricacy, exploring every possible configuration until self-replication and metabolism emerge. Life, then, is the continuation of chemistry by other means. The abundance of potential also explains why astrobiologists search for life, not by looking for Earth itself, but for chemistry's footprints, disequilibrium, reactivity, and molecular asymmetry. On any planet where the atmosphere contains gases that should not coexist, like oxygen and methane, we suspect an active process replenishing them. Such imbalances are thermodynamic signatures of life's metabolism, hints that chemistry has crossed the threshold into biology. The universality of chemical laws ensures that these signs, if present elsewhere, will be recognizable to us. The same periodic table governs every atom in every galaxy. When we look for alien life, we are really looking for ourselves, for the familiar patterns written in a different dialect. Yet the inevitability of chemistry also carries philosophical weight. If the cosmos naturally produces the ingredients of life, then existence itself may be a chemical imperative rather than an anomaly. The atoms do not conspire to make life. They simply follow their tendencies, and life emerges as a byproduct of their obedience. This realization shifts the narrative of creation from miracle to mechanism, a mechanism no less wondrous for its universality. The stars, the dust, the oceans, and the living mind all belong to a single continuum of matter, exploring its own potential. In this sense, chemistry is the universe dreaming of life. From a purely statistical perspective, the numbers are staggering. There are estimated to be over 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars, most with planets. If even a small fraction of those planets host conditions similar to Earth's, the total number of habitable worlds would be astronomical, perhaps 10 to the power of 22 in number. And on each, chemistry would follow the same rules, combining the same atoms into similar molecules, driven by the same flows of energy. The inevitability of chemistry becomes the inevitability of life's possibility. The question, then, is not whether life exists elsewhere, but how often the dice of time have rolled long enough for chemistry to awaken into consciousness. As our instruments probe deeper into space, this inevitability reveals itself in ever more tangible forms. The James Webb Space Telescope has already detected water vapor, carbon dioxide, and methane in the atmospheres of distant exoplanets. Spectral signatures show clouds, winds, and temperature gradients, conditions ripe for complex chemistry. In laboratories, scientists simulate interstellar conditions and watch organic molecules self-assemble on grains of ice, mimicking the chemistry of the early universe. The gap between the cosmic and the biological grows smaller with every experiment. Each new discovery reinforces the same truth. Life's chemistry is not special to Earth. It is written into the laws of the universe. The story of cosmic abundance is therefore not one of chance, but of continuity. From the birth of atoms to the formation of galaxies, from the condensation of planets to the emergence of cells, the same principles operate, the same ingredients recur. Matter does not rest. It evolves, seeking complexity as naturally as rivers seek the sea. The inevitability of chemistry ensures that wherever conditions allow, life's potential will bloom. We live, then, in a universe predisposed to creation. A universe where stars forge the elements, gravity gathers them, and chemistry gives them purpose. Every breath, every heartbeat, every thought is the echo of that universal abundance, the whisper of atoms fulfilling their destiny. From atoms to organisms, the universal pattern. From the cold simplicity of hydrogen to the intricate choreography of DNA, the universe tells one unbroken story. A story of matter learning to organize itself, of energy shaping structure, of simplicity blossoming into complexity. Across 13.8 billion years, the cosmos has followed a pattern so consistent, so profound, that one could almost mistake it for intention. Yet it needs none. The laws of nature alone, gravity, electromagnetism, thermodynamics, and the subtle architectures of atomic interaction are sufficient to explain how chaos becomes form, how atoms become organisms, and how life becomes a mirror for the universe itself. At the smallest scale, the atom stands as the first miracle of organization. It is not a solid sphere, but a dynamic system of probabilities, a dance of electrons around a nucleus that itself is a symphony of quarks and gluons. Each element of the periodic table represents a distinct tuning of this dance, a specific harmony between positive and negative charge, between nuclear force and quantum uncertainty. In these harmonies lie the properties that shape the world. The strength of metals, the transparency of glass, the reactivity of carbon. The atom, stable yet active, is the first living metaphor of matter, poised between balance and transformation, between permanence and possibility. When atoms meet, they do not collide blindly. They respond to the deep logic of energy minimization. Their bonds form not through violence, but through a kind of negotiation, seeking arrangements that yield the least tension, the greatest stability. Molecules, in this sense, are the diplomacy of the universe, the compromises that allow diversity to exist. The geometry of water, the tetrahedral symmetry of methane, the double helix of DNA. Each is an expression of this principle, structure born from the pursuit of equilibrium. Chemistry, therefore, is not random, but purposeful in its direction, and once set into motion, it drives inexorably toward the creation of patterns that persist, replicate, and evolve. In the earliest epochs of planetary history, this drive was unrelenting. On the young Earth, as temperatures cooled and oceans formed, molecules began to interact in vast chemical networks. Lightning, ultraviolet radiation, and geothermal heat provided the energy, while minerals and clays offered surfaces for catalysis. The atmosphere of methane, ammonia, and water vapor became a vast experiment, producing amino acids, sugars, and lipids by the trillions. Each molecule was a small improvisation, a note in a cosmic melody that had begun long before in the hearts of stars. Over time, some combinations proved more stable, more capable of persistence amid turbulence. Self-reinforcing reactions emerged, cycles that drew energy from their surroundings to sustain themselves. Out of chemical noise arose the first whispers of order. The transition from chemistry to biology was not a single event, but a continuum. Somewhere within those ancient networks, molecules began to replicate imperfectly, and in doing so they crossed a threshold. With replication came heredity, and with heredity came evolution, the ability of matter to learn from its own fluctuations. Life began not as an organism, but as a process, molecules exploring the landscape of possibility, competing for stability and efficiency. Those that best maintained their structure amid change persisted. Those that failed dissolved back into the primordial sea. The logic of natural selection, often thought to belong only to biology, is thus rooted in the same thermodynamic laws that govern the stars. Life is the universe refining its own chemistry through feedback. From the first protocells to the microbial empires that followed, complexity grew as a natural consequence of interaction. Cells formed networks, colonies, ecosystems. Cooperation, as much as competition, became a principle of survival. Single-celled organisms joined in symbiosis, giving rise to eukaryotes, a merging of genetic lineages that would eventually produce multicellular life. Every leap in evolution represented a new way of managing energy, of storing information, of resisting entropy. The pattern that had governed atoms and molecules, the emergence of order through energy flow, now played out in living systems on a grander scale. The cell became the atom of life, the basic unit of organization in a biological cosmos. When one steps back to view this pattern over geological time, it reveals a remarkable symmetry. In the physical universe, gravity gathers matter into galaxies and stars. In the biological universe, chemistry gathers molecules into cells and organisms. Both processes transform energy into structure, and both produce complexity that feeds upon itself. The universe's expansion and life's evolution are parallel expressions of the same underlying imperative: to explore every possible configuration of matter that the laws of physics allow. From the spiral arms of galaxies to the spirals of DNA, the geometry repeats, a reflection of how nature builds beauty through recursion. The universality of this pattern extends beyond Earth. Wherever the conditions resemble those of the early Earth, liquid solvents, energy gradients, and time, the same chemical logics are likely to unfold. The methane lakes of Titan, the subsurface oceans of Europa and Enceladus, the red plains of Mars, each is a stage upon which this cosmic narrative may replay itself in variations. Whether or not life has yet taken hold there, the chemistry has already begun. Carbon forms chains, nitrogen bonds to oxygen, water dissolves and transports. If there are organisms beyond Earth, they will not be alien in essence, but fellow expressions of the same universal laws. Their biology will rhyme with ours, because their atoms sing the same song. What makes this pattern truly extraordinary is that it appears to be recursive, life reflecting upon life, matter becoming conscious of its own genesis. Somewhere in the evolutionary chain, the flow of energy through matter gave rise to awareness. The neurons of a human brain, firing in electrochemical rhythms, are descendants of the same atoms that once fused in stars and bonded in clouds. When the mind contemplates the cosmos is, in a sense, thinking about itself. Consciousness is the echo of cosmic evolution, turned inward, the ultimate feedback loop. The universal pattern reaches self-recognition. This continuity between the physical and the mental realms challenges the old division between matter and meaning. The emergence of consciousness does not break the pattern, it completes it. If atoms seek stable configurations and molecules seek replicating ones, perhaps minds seek coherent narratives, patterns of understanding that allow them to survive in the chaos of experience. The brain, after all, is a thermodynamic structure optimized for information processing. Its evolution follows the same logic of efficiency that guides stars and cells. The difference lies only in scale and expression. Where galaxies trade in gravity and light, minds trade in symbols and ideas. Both are vehicles for energy and information, transforming potential into structure. Seen through this lens, the entire history of the universe becomes a single unfolding act of organization. From the quantum fluctuations of the Big Bang to the neuronal firings of thought, complexity has emerged through the interplay of chance and law, of entropy and energy flow. The pattern is fractal, repeated at every scale, from the smallest particle interactions to the grandest cosmic webs. No designer is required, only the consistent application of physical principles over deep time. The universe builds itself through iteration, feedback, and the relentless exploration of what is possible. This understanding does not diminish the wonder of creation. It amplifies it. To realize that the same mathematical symmetries that govern galaxies also govern the folding of proteins is to see the unity behind all phenomena. It implies that life is not an anomaly in the universe, but its natural expression. The laws that shape the stars are the same that shaped us. The hydrogen atom and the human heart are chapters of the same story written in different alphabets. In recognizing this, we begin to understand that biology and cosmology are not separate sciences, but two perspectives on the same phenomenon, the universe becoming self-organizing and self-aware. In the great arc of cosmic history, this pattern continues to evolve. Just as the first stars enriched the galaxy with heavy elements, the emergence of life enriches the universe with new forms of complexity. Ecosystems, cultures, and technologies. Intelligence is merely the latest mechanism by which the cosmos refines its structures, capable of rearranging matter with purpose and foresight. Humanity's exploration of space, our quest to understand the origins of life, and our development of technology are all extensions of the same cosmic impulse that forged the first molecules. We are not outsiders probing an alien universe. We are the universe extending its own reach through curiosity. The journey from atoms to organisms thus reveals a truth at once scientific and spiritual. That life is not a rare accident in a hostile cosmos, but a recurring theme in a universe predisposed to order. The same forces that sculpt galaxies also sculpt DNA. The same balance of chance and necessity that shaped stars also shapes minds. The pattern is universal, the story continuous, and the outcome, consciousness, inevitable once the stage is large enough and time long enough. Every living being is a verse in this cosmic poem, every thought a ripple in the deep current of creation. The atoms that were once dispersed in interstellar clouds now pulse within us, arranged into living circuits of perception and reflection. Through us, the universe has gained eyes to see itself, ears to hear its music, and minds to ponder its meaning. We are not separate from the cosmos, but its living expression, a brief yet luminous pattern in the vast continuum from matter to mind. And as long as energy flows, as long as stars burn and atoms bind, the universal pattern will continue, evolving new forms, new minds, new ways for the cosmos to know itself. The journey from stardust to consciousness is not over. It has only just begun. Nebula theory. Before there were worlds, there were clouds, vast dark curtains of interstellar dust and gas suspended between the stars, illuminated faintly by distant starlight. These molecular clouds, cold and immense, are the wombs of creation. Within them, the raw ingredients of planets, moons, and atmospheres await the touch of gravity. Every world, from the frozen plains of Pluto to the hot winds of Mercury, traces its ancestry to such a nebula. The story of planetary birth begins not with rock and ocean, but with the gentle collapse of a cloud. The nebula theory first proposed in the 18th century by Immanuel Kant and Pierre-Simon Laplace, remains one of the most elegant narratives in all of science. It tells of how solar systems arise naturally from the physics of rotation, condensation, and gravitational symmetry. According to this vision, a great molecular cloud, composed primarily of hydrogen and helium, enriched by the ashes of older stars, begins to contract under its own gravity. Random turbulence, perhaps triggered by the shockwave of a nearby supernova, disturbs the delicate balance between pressure and gravity. The collapse begins slowly at first, then accelerates as mass concentrates toward the center. Angular momentum, once spread across light years, becomes trapped in a shrinking sphere. And as any spinning skater knows, when the arms draw inward, the spin accelerates. The cloud flattens into a rotating disk, the cosmic signature of birth. At the heart of the collapsing nebula, pressure and temperature rise until nuclear fusion ignites, and a new star is born. The surrounding material, unable to fall directly inward due to its angular momentum, forms the protoplanetary disk, a thin, luminous structure of gas and dust encircling the newborn sun. Within this disk, the architecture of the planetary system begins to take shape. Dust grains collide and stick, forming clumps that grow into planetesimals, then into embryonic planets. Over millions of years, the disk evolves into a complex dynamic ecosystem of accreting worlds, migrating orbits, and competing gravitational influences. Out of turbulence emerges order. Out of chaos, the harmony of planetary motion. The beauty of the nebula theory lies in its universality. It explains not only our solar system, but the thousands of exoplanetary systems now observed across the galaxy. Wherever we look, we find disks around young stars, glowing in infrared light as dust absorbs and re-emits stellar radiation. In these disks, astronomers detect rings, gaps, and spiral patterns, signatures of unseen planets forming within. The Atacama Large Millimeter/Submillimeter Array, ALMA, has revealed such disks with astonishing clarity. Concentric structures around stars like HL Tau and TW Hydri that mirror the early history of our own sun. The same processes that shaped Earth are happening elsewhere, in countless variations, confirming that planet formation is a natural outcome of stellar birth. But the nebula theory is more than a mechanism. It is a philosophy of continuity. It reveals how the small is born from the great, how every atom of rock and water on a planet once belonged to a diffuse cloud spanning trillions of kilometers. The sun and its planets are not separate creations, but different expressions of the same collapsing mass. The star claims 99.8% of the system's total matter, while the remaining fraction forms the planets, moons, asteroids, and comets. The debris left behind after the central furnace ignites. Thus, every world is a child of the same stellar event, a fragment of the nebula that gave birth to the star itself. The architecture of a planetary system emerges from this primordial disk, with astonishing diversity. Near the young star, where temperatures soar above 1,000 degrees, only metals and silicates can condense. Farther out, where the light dims and the cold deepens, ices of water, methane, and ammonia solidify. This temperature gradient, known as the frost line, acts as a boundary between rocky and gaseous worlds. Inside it form terrestrial planets, dense, metallic, and small. Beyond it, gas and ice giants gather vast atmospheres around solid cores. The pattern holds not only in our own solar system, but in many others observed by modern astronomy. Physics, impartial and universal, sets the rules by which diversity arises. Yet within that framework, no two planetary systems are identical. Slight differences in disk density, turbulence, or angular momentum can yield radically different outcomes. Some systems harbor hot Jupiters, giant planets orbiting their stars at scorching distances closer than Mercury's path. Others display compact families of super-Earths or chains of resonant worlds dancing in gravitational harmony. This diversity tells us that while the laws of physics are universal, their initial conditions allow infinite variation, a cosmic symphony played on a single set of principles. The nebula theory provides the score, but chance and chaos compose the melody. Our own solar system bears the marks of its turbulent youth. Isotopic evidence from meteorites shows that it formed rapidly, within a few million years of the Sun's ignition. The inner planets, Mercury, Venus, Earth, and Mars, condensed from high-temperature minerals within the inner disk, while Jupiter and Saturn accreted enormous envelopes of hydrogen and helium from the colder outer regions. Uranus and Neptune, slower to form, retained less gas and more ice. Beyond them stretched a vast debris field, the Kuiper Belt, and farther still, the distant Oort cloud, a sphere of comets marking the boundary between our system and interstellar space. This architecture, with its orderly spacing and near-circular orbits, conceals a history of violence, collisions, migrations, and resonances that shaped the planet's present harmony. In the laboratory of the cosmos, the nebula theory has proven itself not merely descriptive, but predictive. It accounts for the angular momentum of planets, their orbital planes, and their compositions. It explains why all major planets orbit in the same direction, why their orbits lie nearly within the same plane, and why the outer planets are volatile rich while the inner worlds are not. It also accommodates exceptions, tilted axes, eccentric orbits, and retrograde moons, as natural consequences of collisions and gravitational interactions. In this sense, the architecture of planetary systems is not a design, but an emergent order, a delicate balance between determinism and chance. What is most remarkable about the nebula model is how it reveals the unity of creation across scales. The formation of planets mirrors the formation of stars, and both echo the structure of galaxies themselves. Spiral arms, protoplanetary disks, and even accretion rings around black holes all follow the same physical laws of rotation, viscosity, and angular momentum conservation. The universe seems to favor the disk, a geometry of equilibrium between collapse and motion, between gravity's inward pull and inertia's outward push. It is as if the cosmos, through endless repetition, finds in this form its most efficient way to build complexity. In this vast continuum, our Earth occupies no privileged position. It is a single pebble orbiting a medium-sized star in a spiral arm of an average galaxy. Yet from this ordinariness arises significance. If planet formation is natural and universal, then the potential for life is widespread. The nebula theory thus bridges astrophysics and biology, linking the birth of worlds to the birth of beings. The same laws that govern the condensation of dust into stone also govern the assembly of molecules into cells. Both are acts of organization in a universe predisposed to create order from chaos. When we gaze upon images of young stars surrounded by glowing disks, we are witnessing the same process that birthed our home 4.5 billion years ago. The light of those distant systems carries our own origin story written in another language, hydrogen and dust becoming suns and worlds. The nebula theory, in its elegant simplicity, unites the heavens and the earth, showing that the birth of worlds is not an isolated miracle, but the inevitable rhythm of a creative cosmos. Every grain of dust, every atom of hydrogen, waits patiently for gravity to call it into motion, to begin again the endless cycle of collapse, ignition, and rebirth. Accretion disks and planet formation. Physics. Every world that drifts through the black sea of space began as dust, particles smaller than smoke, drifting in a great luminous sheet of gas. From that dust, under the invisible hand of gravity, come mountains, oceans, and atmospheres. The path from atom to planet is one of the most extraordinary journeys in nature, for it shows how blind physical laws can sculpt beauty and precision out of chaos. The accretion disk is the crucible in which this transformation occurs, a vast rotating workshop where matter learns to assemble itself into worlds. An accretion disk is born from collapse and motion. When a fragment of a molecular cloud contracts under gravity, it carries with it a trace of the cloud's original rotation. As the material falls inward, angular momentum prevents it from collapsing directly into the center. Instead, it flattens into a disk, an enormous whirlpool of dust and gas encircling the nascent star. Within this spinning structure lies a delicate balance. Gravity pulls the material inward, while centrifugal force resists collapse, and viscous friction redistributes angular momentum through the disk. The result is a self-regulating system that persists for millions of years, feeding the young star while simultaneously spawning planets. In these disks, everything that defines a planetary system is determined. The spacing of orbits, the size of worlds, their compositions and fates. Temperature gradients divide the disk into zones of condensation. Silicates near the blazing star, ices and volatiles farther out. In the inner regions, where heat vaporizes lighter compounds, only refractory minerals can survive, forming grains of rock and metal. These particles, suspended in turbulent gas, collide and stick through electrostatic forces, forming aggregates a few millimeters across. In the outer regions, where cold dominates, grains are coated in ice, making them stickier and able to grow more rapidly. Step by step, through millions of collisions, dust becomes pebble, pebble becomes boulder, and boulder becomes embryo. This slow gathering of matter, known as accretion, is the heartbeat of planetary creation. Each impact between particles dissipates energy and binds them more tightly. Over time, gravitational attraction amplifies the process. As a body grows, its mass increases its pull on nearby material, accelerating its growth. This runaway effect transforms kilometer-sized planetesimals into planetary cores. The physics is relentless. Mass begets mass. Gravity feeds upon itself, and from the friction of chaos arises order. But the disk is no tranquil nursery. It is a place of fierce competition and turbulence, a cosmic storm where fragments collide at tens of kilometers per second. Many are shattered and reabsorbed into dust, while a few survive to grow larger. The physics of these interactions depend upon drag, velocity, and cohesion. In the inner disk, where gas is dense and heat intense, friction slows solid bodies, causing them to spiral inward toward the star. This radial drift poses a paradox. Without efficient mechanisms to overcome it, particles might fall into the star before planets can form. Yet nature, ingenious in her economy, provides solutions. Vortices, pressure bumps, and magnetic instabilities create regions where material gathers and slows, forming traps that allow growth to continue. Within these eddies, dust collects and clumps, like leaves swirling in a whirlpool, the first steps toward worlds. Once bodies reach a critical size, perhaps 100 kilometers across, gravity becomes the dominant architect. These planetesimals act as seeds, sweeping up smaller debris through gravitational focusing. The rate of accretion accelerates exponentially, producing protoplanets that clear their orbital neighborhoods. In the outer disk, where ices add bulk, these protoplanets can reach 10 Earth masses or more, massive enough to capture the surrounding hydrogen and helium, forming the gas giants. Closer to the star, where such gases are scarce, rocky worlds like Earth and Venus emerge. Thus, the physics of temperature and density alone determine the broad outline of planetary architecture. an elegant balance between chemistry and thermodynamics. The dynamics of accretion are governed by energy as much as by mass. Each collision releases heat, melting and differentiating the growing bodies. Iron and nickel sink to form metallic cores, while silicates rise to form mantles and crusts. Volatile elements, trapped in minerals or delivered by icy planetesimals, form the first atmospheres. In this way, accretion is not merely mechanical, but chemical. It sets the stage for the later evolution of planetary geology, magnetism, and climate. The very processes that built the planets also forged their inner structures, the layered symphony of core, mantle, and crust that underlies every terrestrial world. The mathematics of accretion reveal a universe both predictable and chaotic. In principle, one can model the disk using the equations of hydrodynamics, angular momentum transfer, and radiative cooling. Yet, in practice, small differences in initial conditions, a denser region here, a turbulent eddy there, lead to wildly different outcomes. This sensitivity, known as chaotic evolution, means that each planetary system is unique, even though all follow the same physical rules. Our solar system's orderly architecture, with its near-circular orbits and stable resonances, may be a rare outcome of this cosmic lottery. Elsewhere, the dice of turbulence have produced astonishingly varied results. Planets larger than Jupiter orbiting closer than Mercury, twin stars sharing disks, and worlds locked in eccentric tilted paths that defy symmetry. The universe, though governed by law, delights in improvisation. Observations of young stellar systems have provided breathtaking glimpses of these processes in action. Around the star HL Tau, ALMA's radio images reveal a disk laced with concentric rings, gaps carved by emerging planets still hidden within the dust. Each gap marks a gravitational resonance, a place where a forming planet's orbit sculpts the material around it. Other systems, like PDS-70, show even more direct evidence. A glowing blob of heat within the disk, the infrared signature of a planet still accreting gas. Such discoveries confirm that accretion is not theoretical abstraction, but an ongoing reality, repeated endlessly across the galaxy. In every stellar nursery, nature performs this same slow miracle, transforming clouds into systems of suns and worlds. The physics of accretion also connects the smallest and largest scales of the universe. The same equations describe the disks around black holes, neutron stars, and quasars. In each case, matter spirals inward, releasing energy as it falls, while angular momentum drives outflows and jets. The geometry of the accretion disk, thin, rotating, radiative, appears to be the universe's most efficient engine for converting motion into structure. From the vast disks that feed supermassive black holes to the delicate rings that birth planets, the pattern repeats. The laws that sculpt a star system are the same that shape galaxies and quasars. The cosmos builds itself through accretion, a single principle echoed in every act of formation. In the later stages of a disk's life, as the young star stabilizes, radiation and stellar winds begin to clear away the remaining gas. The process is violent but necessary. As the gas disperses, the surviving protoplanets settle into stable orbits, their growth complete. Some collide and merge, forming larger worlds. Others are ejected into interstellar space, wandering forever as rogue planets. The leftover debris becomes asteroids, comets, and dust, the relics of creation. What remains is a planetary system, a star at the center, encircled by worlds and remnants, all obeying the same gravitational rhythm. The disk is gone, but its memory endures in the architecture it leaves behind. To understand accretion is to glimpse the universe's creative logic. The process is at once destructive and generative, collisions that shatter yet build. chaos that begets order. It embodies the paradox of cosmic evolution, that out of the relentless tendency toward entropy arises the local miracle of complexity. Each world is a frozen record of that tension, a fossilized vortex of energy and matter. When we walk upon the Earth, we stand on the cooled remnants of ancient collisions. Our continents and mountains born from the same forces that still sculpt planets around distant stars. And within that understanding lies a profound unity. The same gravity that gathered the dust into Earth's orbit also holds us to its surface. The same thermodynamics that melted the early planet now powers the core's convection and magnetic field. We are not separate from the processes that shaped our world. We are their continuation. The atoms in our bodies were once part of a disk, warmed by a newborn sun, caught in the swirl of accretion. To study planetary formation is to trace our own origins, to see that the physics that made the worlds also made us. Thus, the accretion disk stands as one of nature's most majestic inventions, a structure that turns the abstract language of gravity and motion into tangible form. Within its spirals, the universe rehearses the art of creation, sculpting countless worlds from dust and gas, each a new variation on the same eternal theme. Every planet, every moon, every asteroid is a note in that cosmic composition, the residue of a dance that began billions of years ago and continues wherever stars are born. The disk fades, the light clears, and in its place orbit the enduring children of its turbulence, the worlds. Migration, chaos, and planetary diversity. If the nebula disk is the cradle of worlds, then migration is their first great journey, a restless reshuffling of orbits that turns symmetry into surprise. The planets we see today, both in our solar system and across the galaxy, are not where they were born. Their paths have been sculpted by invisible exchanges of energy and momentum, by collisions, resonances, and gravitational tides. The serene order of the night sky conceals a past of turbulence and drift, a cosmic choreography driven by the laws of orbital dynamics. The result is astonishing diversity, systems of worlds more strange and varied than imagination once dared to conceive. When the first exoplanets were discovered in the 1990s, the astronomical community was stunned. The very first 51 Pegasi b defied every expectation. A gas giant larger than Jupiter, orbiting its star in just 4 days. According to classical models, such planets should form far from their stars, where temperatures are cold enough for ices to condense. Yet here was a hot Jupiter, skimming the stellar surface, its atmosphere glowing with heat. The revelation forced a profound rethinking of planetary evolution. The orbits of planets, it became clear, were not fixed. They could move, drift, and migrate across enormous distances. The mechanism of this migration lies within the disk itself. In the early stages of formation, the protoplanetary disk is a living system of gas and dust in motion. As a planet coalesces, its gravity creates spiral waves in the surrounding gas, much like ripples from a stone dropped into water. These waves exert torques on the planet, stealing angular momentum from one side while adding it on the other. If the inward pull outweighs the outward push, the planet spirals toward the star. If the reverse is true, it drifts outward. This phenomenon, known as disk-driven migration, reshapes entire systems in just a few million years, a blink in cosmic time. There are several regimes of migration, each governed by mass and disk density. Type 1 migration affects smaller Earth-sized worlds embedded in the gas. They feel the tug of asymmetric waves and drift inward rapidly unless trapped by pressure gradients or resonances. Type 2 migration occurs when a massive planet, like Jupiter, carves a gap in the disk and migrates with it, moving as the gas itself slowly drains toward the star. Type 3, or runaway migration, can occur under extreme conditions, when the planet's mass and the disk's density interact chaotically, sending it spiraling inward in a catastrophic plunge. These processes, observed indirectly through exoplanet demographics, explain why so many giant planets orbit perilously close to their stars, victims of the migration that followed their birth. But migration is only the beginning of planetary chaos. Once the gas dissipates and the disk fades, gravitational interactions among the remaining planets continue to sculpt their orbits. Close encounters can fling planets into new trajectories, some inward toward the star, others outward into deep space. A slight nudge at the wrong moment can amplify over time into radical change, a phenomenon known as orbital instability. Chaos, in this context, does not mean randomness, but sensitivity, the exponential growth of small differences. Two identical systems, starting from nearly identical conditions, can evolve into entirely different architectures. This is why no two planetary systems, even if born from similar disks, are ever the same. Our own solar system bears silent witness to such instability. In its youth, Jupiter and Saturn likely migrated inward and then outward again, a motion that profoundly reshaped the inner system. This grand tack hypothesis suggests that Jupiter once ventured as close as Mars's orbit, before reversing course due to resonance with Saturn. As the two giants interacted, their gravitational tugs scattered asteroids, stirred the planetesimal disk, and curtailed Mars's growth, leaving it smaller than expected. Later, during the so-called late heavy bombardment, migrating outer planets destabilized the orbits of comets and asteroids, sending a storm of impacts into the inner solar system. Our moon's cratered face preserves the scars of that chaotic epoch. Beyond our system, the diversity of outcomes is staggering. Some planetary systems, like TRAPPIST-1, pack 7 Earth-sized worlds into orbits smaller than Mercury's, each locked in delicate resonance with the next, a cosmic clockwork of perfect rhythm. Others, such as Kepler-11, host compact families of super-Earths, orbiting within a few million kilometers of their stars. Meanwhile, systems like HD 80606 harbor planets on extreme, elongated orbits that swing them from icy cold to blistering heat within days. These architectures reveal a universe of experimentation, where the same physical laws produce endless variation. The symmetry of the nebula model gives rise to asymmetry through the dynamics of time. Underlying this diversity is the interplay between order and chaos, between the stabilizing geometry of orbital resonance and the disruptive energy of gravitational encounters. Resonances occur when orbital periods form simple ratios, 2:1, 3:2, and so on, allowing planets to exchange angular momentum in a rhythmic dance. These configurations can stabilize systems, as in Jupiter's moons Io, Europa, and Ganymede, which remain in perfect resonance, their orbits locked in a perpetual symphony. Yet resonances can also destabilize, amplifying perturbations until orbits cross and collisions occur. The same mechanism that creates harmony can, under different conditions, compose destruction. The beauty of planetary dynamics is its universality. The same equations of motion that describe the orbits of our solar system's planets apply equally to binary stars, asteroids, and exoplanetary systems, thousands of light years away. Newton's and Kepler's laws, refined by Einstein's relativity, govern all orbital evolution, yet the outcomes are infinitely varied. Planetary systems evolve like ecosystems, shaped by initial conditions, feedback loops, and chance events. They are deterministic in principle, but unpredictable in detail. In this sense, the diversity of worlds is the natural result of the universe's deep logic, law without repetition. The discovery of thousands of exoplanets has transformed our understanding of what normal means. We once imagined that our solar system, with its orderly spacing and circular orbits, represented the cosmic norm. Now we know it is only one variation among countless others. Some stars host planets with orbital periods of mere hours, skimming their stellar surfaces. Others possess frozen giants wandering hundreds of astronomical units away. Some systems contain planets that share orbits, others that orbit backward relative to their star's rotation. There are planets tidally locked to eternal day and night, planets made of diamond, planets bathed in oceans of lava. The diversity is not random, but the inevitable expression of physics exploring every allowable configuration. The migration of planets also plays a profound role in determining which worlds may host life. A migrating giant can scatter smaller, potentially habitable planets, or conversely, shepherd them into stable regions. In our solar system, Jupiter's gravitational influence may have protected Earth by deflecting comets and asteroids, a cosmic shield forged by migration's aftermath. But in other systems, hot Jupiters might sterilize inner worlds or prevent them from forming at all. Thus, the same process that creates diversity also sets the stage for habitability. Life owes its chance not to perfect stability, but to a balance between chaos and order. From a philosophical perspective, planetary migration mirrors evolution itself, adaptation through motion, diversity born of instability. Just as biological systems evolve by responding to environmental pressures, planetary systems evolve through gravitational feedback. Orbits shift, collisions reshape landscapes, and out of destruction emerges new possibility. In both cases, complexity arises from disequilibrium. The universe does not seek stillness. It thrives on change. Recent simulations suggest that migration is not only common, but essential. Without it, giant planets would rarely form, and terrestrial worlds might remain small and dry. Migration redistributes materials, water, carbon, silicates, across vast distances, enriching inner worlds with the ingredients for life. In this sense, chaos is creative. The same gravitational turbulence that threatens to destroy planets also delivers them the means to live. The boundary between catastrophe and creation blurs in the physics of planetary motion. Observations continue to reveal how migration shapes systems in real time. The Kepler and TESS missions have mapped thousands of planetary orbits, showing how common resonance chains and compact configurations are. The James Webb Space Telescope, with its infrared precision, now probes exoplanet atmospheres, tracing their origins to the disks where migration began. Each data point, each light curve, adds another verse to the story of cosmic variety. A universe endlessly remixing its materials into new harmonies. Migration and chaos together ensure that the cosmos will never repeat itself. Each star is a laboratory of creation, each planetary system a unique outcome of shared rules. The diversity we see, of orbits, compositions and climates, is the natural consequence of the universe's restlessness. Gravity does not build worlds in stillness, but in motion, sculpting order through instability. The result is an infinity of possibilities. A cosmos, where every world is an experiment in form and survival. Our own Earth, stable and temperate, is one such outcome, the fortunate survivor of migration's tumult. Its orbit, neither too eccentric nor too circular, offers the long calm in which life could flourish. Yet beneath that calm lies a legacy of chaos. The migrations of the giants, the bombardments of comets, the tilting of the axis. Without them, Earth might never have become a living world. Thus, the diversity of planets is not noise in the cosmic order. It is the order itself, the living expression of physics' capacity for invention. The birth of worlds, then, is not a single act, but an ongoing evolution. Planets are not fixed spheres, but dynamic participants in a cosmic narrative of motion and transformation. Their migrations, collisions, and variations reveal a universe that is not mechanical, but creative, where law and chance conspire to produce endless novelty. To gaze upon the exoplanet catalogue is to see the imagination of nature written in gravity's hand. A library of worlds, each page composed of orbit, chemistry, and time. In their diversity we find not confusion but confirmation, that the cosmos, in all its apparent chaos, is perfectly ordered to create difference. The role of moons, magnetic fields, and rotation. When a world is born, its destiny is not determined by size or composition alone. The deeper architecture of a planet, its climate, stability, and capacity for life, is profoundly influenced by subtler companions and forces. The rhythm of its rotation, the invisible armor of its magnetic field, and, in some cases, the loyal presence of a moon. These elements work in concert, like hidden engineers maintaining equilibrium in an otherwise chaotic cosmos. A planet without them may exist, but a planet with them can endure. The balance of rotation. Every planet spins, and in that spin lies both its day and its identity. Rotation is the first inheritance of a world, a relic of its formation within the protoplanetary disk. As planetesimals collided and merged, angular momentum was conserved, imprinting upon each newborn world a unique rotational speed and axis tilt. These spins vary wildly across the solar system. Jupiter turns once every 10 hours, flattening at its poles under the strain of centrifugal force, while Venus rotates so slowly and backward that its day outlasts its year. These differences are not trivial curiosities. They shape the very nature of each planet's surface and atmosphere. Rotation governs a planet's climate engine. The Coriolis effect, arising from spin, divides atmospheric flows into jet streams, cyclones, and stable circulation patterns. Without it, air and oceans would move in simpler, less predictable currents, and weather might grow more extreme. Earth's 24-hour rotation period creates a dynamic but balanced climate. Not too turbulent, not too still. Were our planet to rotate twice as fast, winds would howl at hurricane speeds across the continents. Were it to rotate half as fast, deserts and frozen poles might dominate. Rotation is thus a delicate tuning between chaos and calm, regulating the heartbeat of weather. The tilt of a planet's rotation axis, its obliquity, further defines its seasons. A small tilt yields minimal variation, as on Jupiter. A large one, like Uranus's 98 degrees, creates extreme seasonal swings that last decades. Earth's moderate tilt of 23.5 degrees produces the gentle rhythm of seasons that sustain global biodiversity. Yet obliquity is not fixed. It wobbles over tens of thousands of years due to gravitational interactions with other planets and moons. Without stabilizing influences, a planet's tilt can wander chaotically, leading to climate catastrophes, alternating between frozen and scorched epochs. Here, the moon becomes Earth's silent stabilizer, the lunar companion. Our moon is far more than a luminous ornament in the night sky. It is a dynamic partner, a relic of cosmic violence that reshaped the young Earth. Most evidence points to a titanic collision 4.5 billion years ago, when a Mars-sized body, often called Theia, struck the proto-Earth. The impact vaporized rock, forming a disk of molten debris that quickly coalesced into the moon. From that moment onward, the Earth-Moon system became a double world, bound by gravity, locked in mutual evolution. The moon's gravitational pull stabilizes Earth's axial tilt, limiting its variation to only a few degrees. Without this stabilizing torque, simulations suggest our tilt might fluctuate chaotically between 0 and 85 degrees, transforming Earth from habitable to frozen, and back again over geological timescales. The moon, by its sheer mass and proximity, acts as a gyroscopic anchor, maintaining the rhythm of seasons and the long-term stability of climate. Its presence may well have been a prerequisite for complex life to evolve and persist. Beyond stability, the Moon also drives motion. Its gravitational attraction raises tides in Earth's oceans, pulling the waters as the planet rotates beneath it. These tides sculpt coastlines, mix nutrients, and create tidal zones. Habitats that may have nurtured the first steps of life onto land. They also act as a planetary brake. As tidal friction dissipates energy, Earth's rotation gradually slows, lengthening the day by milliseconds each century. At the same time, the Moon drifts outward, receding at a rate of about 4 centimeters per year. Over billions of years, this slow dance has shaped the tempo of our planet's evolution, linking the rhythm of life to the clockwork of celestial mechanics. Not all worlds are blessed with such companions. Mars's 2 tiny moons, Phobos and Deimos, are captured asteroids too small to stabilize its tilt, leaving the Martian climate prone to chaotic oscillations. Venus and Mercury have none at all. Among the exoplanets, moons remain difficult to detect, but their importance is increasingly recognized. A large moon can regulate spin, drive internal tides, and perhaps sustain subsurface oceans by heating the interior through gravitational flexing, as seen on Jupiter's moon Europa and Saturn's Enceladus. In these icy worlds, tides have turned cold geology into warm chemistry, proving that life's potential may extend far beyond the temperate surfaces of terrestrial planets. Magnetic fields, the invisible shields. If rotation and moons shape a planet's rhythm, then magnetic fields guard its survival. Generated by the movement of conductive material in a planet's core, molten iron on Earth, metallic hydrogen on Jupiter. These fields create invisible cocoons that deflect charged particles from the solar wind. Without them, atmospheres erode, radiation intensifies, and habitability withers. Earth's magnetic field arises from the geodynamo, a self-sustaining loop powered by heat and rotation. As the planet cools, convection in the liquid outer core drives the circulation of charged particles, while the planet's spin organizes these flows into a coherent field. The result is a dipole structure, north and south magnetic poles, extending tens of thousands of kilometers into space. The magnetosphere captures solar wind particles, funneling them toward the poles where they create the auroras, visible reminders of the invisible shield that protects us. The field's role in preserving our atmosphere cannot be overstated. Mars, once thought to have oceans and a thicker atmosphere, lost its magnetic field billions of years ago as its core solidified. Without protection, the solar wind stripped away the Martian air, leaving behind a desiccated world. Venus, despite its similar size to Earth, also lacks a global magnetic field. Its dense atmosphere survives only because of its thickness, but its surface is a hellscape of pressure and heat. In contrast, Earth's magnetic field has endured for billions of years, sustaining a temperate climate and shielding the fragile biosphere from lethal radiation. Magnetic fields also influence planetary evolution in subtler ways. They modulate atmospheric escape, interact with stellar winds, and affect chemical reactions in the upper atmosphere. On gas giants like Jupiter and Saturn, enormous fields generate dazzling auroras thousands of kilometers wide, powered by the motion of charged particles along magnetic lines. In exoplanetary systems, magnetic interactions between stars and close-in planets may produce detectable radio emissions, a potential signature of habitability. The presence of a strong field could mark the difference between a living world and a sterile rock. Rotation, once again, lies at the heart of this magnetic vitality. A planet must spin fast enough to sustain the geodynamo. Slow rotation can weaken the flow of molten material, and allow the field to collapse. Earth's 24-hour rotation provides just the right energy to keep its core churning. Mercury, though small and slow, retains a faint field due to a partially molten core. Meanwhile, Venus, whose day lasts 243 Earth days, lacks the dynamo entirely. The link between spin and magnetism is profound. Without rotation, there is no shield. Without a shield, no sustained atmosphere. Without an atmosphere, little hope for life. The symphony of interdependence. Taken together, moons, magnetic fields, and rotation form a triad of planetary harmony, stabilizing, shielding, and synchronizing. Each influences the others in subtle feedback loops. A moon's tidal pull can maintain core motion, aiding the dynamo. Rotation controls both magnetic generation and atmospheric balance. The magnetic field, in turn, helps preserve the conditions necessary for liquid water and stable climates. The interdependence of these factors transforms what might otherwise be barren spheres into enduring worlds. Consider the Earth again, not as a special exception, but as a model of equilibrium. Its moderate rotation sustains a day-night cycle conducive to life. Its moon guards its tilt and seasons. Its magnetic field shelters the biosphere from solar wrath. This synergy is not inevitable, but emergent. The outcome of billions of years of coincidence refined into stability. In this balance lies the secret of habitability, a recipe that may be rare, but not unique in the galaxy. Astrobiologists increasingly search for these triads in exoplanetary systems. Planets with signs of stable rotation and magnetic activity, orbiting stars of gentle variability, stand out as promising candidates. If future telescopes detect moons around such worlds, it will strengthen the case for life. For in the end, habitability is not a single condition, but a symphony, an orchestration of orbital dynamics, internal heat, and magnetic resilience. Rotation, magnetism, and moons remind us that planets are not static or solitary. They are dynamic systems in constant dialogue with their stars and satellites. Their fates depend as much on invisible forces as on visible matter. A planet may have oceans and air, yet without the protection of a field or the guidance of a moon, it may drift into chaos. The cosmos is littered with such examples, worlds nearly right, yet just slightly off balance. In this understanding lies a deeper truth, that habitability is not merely about chemistry or distance from a star, but about harmony, a long, fragile negotiation between motion and stability, energy and protection. The moon that lifts our tides, the magnetic field that shields our air, and the spin that defines our day are not coincidences, but interconnected expressions of the same cosmic law. Systems survive when their parts cooperate. In the birth of worlds, this cooperation is rare but not miraculous. It is the outcome of time, gravity, and persistence. Where these conditions arise, the silence of space gives way to the hum of living cycles, the whisper of tides, the flicker of auroras, the turning of days. A world with such balance becomes not just a planet, but a home. Exoplanet statistics and the new cosmography of life. For most of human history, the stars were silent, distant, eternal, and seemingly uninhabited. We looked up and wondered whether other worlds orbited those distant suns, but the evidence lay beyond the reach of our instruments. It was only in the last generation that the veil lifted, and the cosmos revealed itself as a galaxy of planets. What began as a faint wobble in a star's light has grown into a revolution of cosmic proportions. The discovery that worlds are not rare jewels but common currency. The universe, it turns out, is a builder of planets. The age of exoplanet discovery began modestly in 1995, when Michel Mayor and Didier Queloz announced the detection of 51 Pegasi b, a gas giant orbiting a sun-like star. The technique they used, measuring tiny shifts in the star's spectrum due to the gravitational tug of an unseen planet, opened a new era. Soon other hot Jupiters followed, massive worlds hugging their stars so tightly that their years lasted only days. These early detections shocked astronomers, defying traditional theories of planet formation. Yet as telescopes improved and methods multiplied, the diversity of planetary systems grew beyond imagination. The Milky Way, once thought to be sprinkled with a few isolated systems like ours, was revealed to be overflowing with them, billions upon billions. The scale of this revelation is staggering. The Kepler Space Telescope, launched in 2009, monitored 150,000 stars for subtle dips in brightness, signs of planets passing across their stars' disks. Over its mission, Kepler confirmed more than 2,600 exoplanets and identified thousands more candidates. When the data were analyzed statistically, the results were transformative. Roughly 1 in every 5 sun-like stars hosts an Earth-sized planet in its habitable zone, the region where liquid water could exist. Extrapolated across the galaxy's 200 billion stars, this implies tens of billions of potentially habitable worlds. Our solar system is not exceptional. It is typical. Other methods have added to this grand census. The radial velocity technique detects the wobble of stars, revealing massive planets in close orbits. Transit timing variations measure slight irregularities in the timing of planetary transits, unveiling additional worlds in multi-planet systems. Direct imaging has captured faint glows from giant exoplanets orbiting far from their stars, while gravitational microlensing has revealed rogue planets wandering alone through interstellar space. Together, these techniques paint a portrait of a galaxy brimming with planetary architectures, from compact systems of super-Earths to sprawling families of gas giants. Planetary diversity is not an exception, but the rule. Statistically, the most common type of planet in the galaxy is not one we have in our own solar system. Between Earth and Neptune in size lies a class of worlds called super-Earths and mini-Neptunes. Planets with masses 2 to 10 times that of Earth, often possessing thick atmospheres or deep oceans. These worlds seem to dominate planetary demographics, suggesting that nature favors intermediate sizes over extremes. Some may be water-rich, others rocky, and still others shrouded in hydrogen. A spectrum of possibilities unimagined before Kepler. The familiar categories of Earth-like and Jupiter-like now appear as mere boundaries in a far broader landscape. From these discoveries emerges a new cosmography, a map not of stars but of worlds. The Milky Way is no longer a glittering field of suns, but an ocean of planetary systems, each with its own internal logic and history. Some, like TRAPPIST-1, pack multiple Earth-sized planets in tight orbits, each potentially capable of retaining water and atmosphere. Others, like HR 8799, showcase massive young planets in wide arcs, still glowing from the heat of formation. Even binary and trinary stars, once thought hostile to stable orbits, host planets that weave through complex gravitational harmonies. The notion that our solar system's structure was unique has dissolved into a humbling realization. The universe has built its architecture in endless variation. Exoplanet statistics also reveal the deep relationship between stellar type and planetary abundance. Small, cool stars, known as red dwarfs, make up nearly 3/4 of all stars in the galaxy. And observations show they frequently host planets, including those in their habitable zones. Because these stars burn slowly, with lifespans reaching trillions of years, they may serve as the most enduring havens for life. The TRAPPIST-1 system, orbiting a red dwarf only 39 light-years away, contains 7 terrestrial planets, 3 within the habitable zone. If life can adapt to the flare activity of such stars, it might thrive there for eons longer than on Earth. Yet the raw abundance of planets is only the beginning. The new cosmography also challenges our assumptions about habitability. Worlds once dismissed as barren may harbor life beneath ice or in exotic chemistries. Tidal heating, caused by gravitational flexing from a host planet or moon, can keep subsurface oceans liquid, even in the cold outer reaches of a system. Jupiter's moon. Europa and Saturn's Enceladus demonstrate this principle within our own backyard. Exoplanets with similar configurations may exist by the millions, each with oceans sealed beneath frozen crusts, awaiting the spark of biology. Habitability, we now know, is not confined to temperate surfaces, but may extend wherever energy and chemistry can coexist. The data also reveal the dynamic nature of planetary systems over time. By studying young stars surrounded by dusty disks, astronomers can trace the evolution of planets from infancy to maturity. Infrared surveys show how disks dissipate, how orbits migrate, and how atmospheres evolve under the influence of stellar radiation. These observations, combined with statistical modeling, have turned exoplanet research into a new kind of cosmic archaeology. The reconstruction of planetary histories from the faintest of clues. Each world is a fossil in motion, preserving the story of its birth and transformation. Beyond their scientific implications, these discoveries reshape humanity's perspective. For centuries, the question, "Are we alone?" was a philosophical speculation. Now it is an empirical one. The numbers suggest that life's laboratory extends across the entire galaxy. Even if only a tiny fraction of habitable worlds develop life, the total could still number in the millions. The Drake equation, once a speculative exercise, now has data to fill its first terms. The fraction of stars with planets, the number of planets per star, the proportion in habitable zones. The result is an overwhelming probability that life, in some form, has taken root beyond Earth. The James Webb Space Telescope, JWST, has carried this search into a new frontier: the analysis of exoplanet atmospheres. By capturing starlight filtered through a planet's atmosphere during transit, JWST can detect spectral fingerprints of molecules such as water vapor, carbon dioxide, methane, and ozone. These are the chemical whispers of habitability, and possibly of biology. Already, JWST has detected water in the atmospheres of multiple exoplanets, some smaller than Neptune, confirming that the chemistry of life is widespread. Future instruments, such as LUVOIR and HABEX, aim to go further, capturing direct images of Earth-like worlds and searching for biosignatures, gases like oxygen or methane out of equilibrium, betraying the presence of life. As data accumulates, a pattern emerges. The universe is not empty, but fertile. The same processes that forged our world operate everywhere. Planetary formation is universal, and habitability is a continuum, not a narrow band. The Goldilocks zone, once a metaphor for Earth-like comfort, now expands into a multidimensional concept including temperature, chemistry, magnetism, and time. Life's domain may include sulfuric skies, methane seas, or subterranean oceans. Biology, it seems, is not a rare aberration, but a strategy the cosmos employs wherever energy flows and matter can organize. This new cosmography of life does more than expand our catalogue of planets. It expands our imagination. For the first time, humanity possesses a statistical framework for existence itself. We can quantify our cosmic context. One galaxy, 200 billion stars, trillions of planets, and among them, a fraction where molecules awaken. The numbers do not diminish us, they ennoble us. To exist within such abundance is to participate in the universe's grand experiment in creation. Each new discovery of a world, each faint dip in a star's light, is a note in the ongoing symphony of cosmic genesis. The astronomer Carl Sagan once wrote that the number of planets may be greater than the number of stars. Today we know this is true. The night sky is not a wilderness of solitude, but a vast archipelago of worlds. Some glow like embers, others shimmer with oceans and clouds, each orbiting its own sun in quiet grace. To look upward is no longer to peer into emptiness, but into potential. A cosmos where the seeds of life are scattered like dust, awaiting only the right conditions to bloom. Thus, the discovery of exoplanets has transformed cosmology into cosmography. A map not merely of where things are, but of what might live there. We now inhabit a universe known to be alive with possibility. The stars no longer shine upon us alone. They shine upon innumerable worlds, each with its own dawns and twilights, its own chance to dream. In that realization, the human perspective shifts irrevocably. We are not the exception, but the example. One voice in a galactic chorus of worlds becoming aware. The concept of the habitable zone in theory and observation. In the vast expanse of the cosmos, where countless worlds circle countless suns, one question defines our search for company. Where can life exist? The answer begins with a deceptively simple idea. The habitable zone. The region around a star where conditions allow liquid water to persist on a planet's surface. Water, that most familiar of substances, is the cosmic solvent of life. It mediates chemistry, stabilizes climate, and transports energy. Wherever water remains liquid, the potential for life arises. Thus, the habitable zone is not merely a mathematical boundary. It is the first map of life's possible domains in the universe. The concept has deep roots. In the early 20th century, scientists such as Harlow Shapley and Hubertus Strughold speculated about life belts around stars, regions not too hot, not too cold, where life as we know it could survive. In the 1950s, this idea evolved into a more formal notion of a circumstellar habitable zone, CHZ, based on the physics of radiation balance. The defining principle was straightforward. A planet's temperature depends on the energy it receives from its star and the rate at which it radiates heat back into space. Too close, and the oceans boil away. Too far, and they freeze solid. The habitable zone lies in between. The Goldilocks region, where water can flow and clouds can form, where rivers carve landscapes and seas cradle biology. For our Sun, the classical habitable zone extends roughly from 0.95 to 1.67 astronomical units, encompassing Earth and marginally Mars. Venus, just 30% closer to the Sun, receives nearly twice the solar energy, and long ago crossed the threshold into runaway greenhouse conditions. Its atmosphere, thick with carbon dioxide, traps heat so effectively that its surface glows at 460 degrees Celsius. Mars, though it once had rivers and lakes, lies near the outer edge. Its thin air cannot retain enough warmth to keep water stable. Earth, suspended between inferno and frost, occupies the narrow zone, where the delicate balance of temperature, pressure, and atmospheric composition allows oceans to endure. It is a cosmic sweet spot, but one far more intricate than early models imagined. Modern science has refined the concept dramatically. The simple geometry of distance now gives way to a web of feedback mechanisms that expand or contract the habitable zone's limits. The composition of a planet's atmosphere, its greenhouse gases, cloud cover, and albedo can shift the zone significantly. A thick carbon dioxide blanket, as on early Mars, can extend habitability outward. A bright reflective surface can push it inward. The internal heat of a planet, driven by radioactive decay or tidal flexing, can sustain liquid water beneath ice even outside the classical zone. Conversely, intense stellar radiation or tidal locking can destroy habitability within it. The habitable zone is thus not a fixed ring, but a living boundary. Dynamic, conditional, and deeply contextual. Observations from missions like Kepler and TESS have turned the theoretical into the tangible. Hundreds of exoplanets now known reside within their stars' habitable zones, some even Earth-sized. Systems like Kepler 186f, orbiting a red dwarf, and Kepler 452b, orbiting a Sun-like star, are prime examples. Yet each challenges the simplicity of the original definition. Kepler 186f, though within its star's habitable zone, may be tidally locked. One hemisphere in perpetual daylight, the other in eternal night. Kepler 452b, slightly larger than Earth, may have an atmosphere thick enough to trigger a runaway greenhouse. These examples remind us that distance alone does not define habitability. It is the interaction of energy, chemistry, and time that matters. Red dwarf stars, the most numerous in the galaxy, further complicate the picture. Their habitable zones lie so close that planets orbit in just days or weeks, often becoming tidally locked. Such worlds experience extreme conditions: blazing day sides, frozen night sides, and volatile atmospheres whipped by stellar flares. Yet recent climate models suggest that if these planets possess thick atmospheres or deep oceans, heat could redistribute evenly enough to sustain temperate regions. The habitable zone, in other words, may survive even under alien circumstances. Nature appears endlessly inventive in finding ways to preserve the possibility of life. A broader concept has therefore emerged: the extended habitable zone, a continuum rather than a narrow belt. This includes subsurface environments, exomoons warmed by tidal heating, and even rogue planets adrift in interstellar space, but insulated by thick atmospheres or geothermal heat. Jupiter's moons Europa and Ganymede, and Saturn's Enceladus, demonstrate this principle nearby. Beneath their icy crusts lie global oceans kept warm by tidal flexing, possibly containing hydrothermal vents like those that once sparked life on Earth. In the cosmic context, the habitable zone may no longer orbit stars alone. It may exist wherever energy and liquid water coexist. Even in eternal darkness, from a planetary perspective, the habitable zone is not only spatial, but temporal. Stars evolve. As they age, they grow brighter, shifting their zones outward. The Sun's habitable zone has already moved slightly since Earth's formation, and in 1 billion years, rising luminosity will push it beyond our orbit, evaporating the oceans. Habitability, therefore, is a moving target, a window of opportunity, not a permanent state. This temporal fragility adds urgency to the cosmic narrative. Life must arise and adapt within the brief epoch when conditions align. The Earth's biosphere, in this sense, is not eternal but transient, a phase in the star's long evolution. The refinement of the habitable zone has also introduced chemical habitability. The recognition that alternative solvents and biochemistries could extend life's domain. On worlds too cold for water, methane or ammonia might serve as liquid media. Titan, Saturn's giant moon, exemplifies this possibility. Its methane lakes and nitrogen-rich atmosphere form a laboratory for prebiotic chemistry. Elsewhere, supercritical carbon dioxide or formamide could play similar roles. These ideas stretch the habitable zone beyond temperature to chemistry itself, suggesting that life, if it exists elsewhere, may not mirror terrestrial biology. The universe may host forms of life as diverse as its stars. In observation, the habitable zone has become the guidepost for exploration. The James Webb Space Telescope, JWST, LUVOIR, and HabEx are all designed to probe exoplanet atmospheres within these regions, seeking spectral signatures of water, carbon dioxide, oxygen, and methane. These molecules, especially when found together in disequilibrium, are hallmarks of biological processes. Detecting them on another world would mark one of the greatest milestones in science. The moment when the concept of the habitable zone becomes not theoretical, but inhabited. Each observation brings us closer to answering the question that haunts every night sky. How many of these zones are truly alive? Philosophically, the habitable zone represents more than a boundary of temperature. It symbolizes the balance that defines existence itself. It is the physical manifestation of moderation. Not too much, not too little. A harmony between energy and fragility. In this sense, the concept echoes the ancient notion of the middle way, the equilibrium where extremes meet and life finds stability. The cosmos, in its immensity, produces chaos and void, fire and ice. Yet within narrow ranges of condition, it produces harmony, complexity, and mind. The habitable zone is that harmony writ large, a reminder that balance is the engine of creation. As our knowledge deepens, even the boundary between habitable and uninhabitable becomes blurred. We now recognize habitability gradients, transitions rather than thresholds. A planet's climate can oscillate between stable and unstable states, as seen in Earth's own history of ice ages and greenhouse epochs. Life, once established, can alter these boundaries through feedback. Photosynthesis reshapes atmospheres, cooling or warming a world, effectively moving the habitable zone around its own biosphere. The concept, once static, becomes participatory. Life defines its own space of possibility. The zone of habitability is not merely discovered, it is created. The deeper we explore, the more the universe reveals itself as a continuum of conditions, rather than a dichotomy of life and lifelessness. Some worlds may hover on the edge of viability, their oceans frozen beneath thin shells, their skies trembling between condensation and evaporation. Others may bloom briefly, then fade as their stars evolve. The cosmos is a field of experiments, and the habitable zone is its arena. Each planet represents a trial, each epoch a test. The sheer number of worlds ensures that life will find its footing somewhere, again and again. And so the idea of the habitable zone, once a geometric curiosity, has become a guiding principle of modern astrobiology, a synthesis of physics, chemistry, and time. It binds together the cold mathematics of radiation with the warm hope of biology. It transforms astronomy into a search for mirrors, for worlds where seas move, clouds gather, and perhaps something looks back. In mapping these zones, we are, in truth, mapping our own possibilities, the conditions under which consciousness itself can arise from matter. In the end, the habitable zone is not only out there, it is here. The narrow window of equilibrium that Earth occupies, the balance we must preserve. Our world reminds us that habitability is fragile, not guaranteed by distance but maintained by stewardship. As we extend our gaze across the galaxy, the lesson returns home. To remain habitable is to remain balanced, adaptive, and aware. The habitable zone is both a cosmic condition and a moral metaphor, a reminder that life, anywhere, is the product of harmony between forces vast and minute. When future explorers find that first blue dot orbiting another sun, its oceans gleaming in reflected light, we will understand at last that the habitable zone is not a line on a chart, but a promise written into the fabric of the cosmos. It is the universe's quiet declaration that wherever energy flows gently enough and matter holds together long enough, life will try to begin. The stars are not indifferent after all. They are invitations, each surrounded by a narrow ring of possibility, waiting for consciousness to emerge and know itself again. The origin of life on Earth. Long before DNA, before cells, before even the whisper of metabolism, there was only the restless Earth, a young world turning beneath a faint sun, wrapped in volcanic haze and the ceaseless roar of storms. Its surface shimmered with vast oceans newly condensed from the cooling atmosphere, and upon those oceans fell the elements of creation: carbon, nitrogen, hydrogen, oxygen, phosphorus, sulfur, the alphabet of life. In that ancient epoch, nearly 4 billion years ago, the Earth was both hostile and fertile, a planetary laboratory where chemistry began to dream of biology. It was here, in warm ponds, tidal pools, and deep-sea vents, that life's prelude unfolded. Charles Darwin, in an 1871 letter to his friend Joseph Hooker, imagined some warm little pond where life's first spark might arise, with ammonia and phosphoric salts, light, heat, electricity, and so on present. It was a humble vision, yet profoundly prescient. Darwin's intuition captured the essence of prebiotic chemistry, that life need not have been born fully formed, but could emerge from the self-organization of simple molecules under the right conditions. At the time, such an idea was speculation, for biology then lacked the chemical and physical understanding to test it. But with the rise of molecular science in the 20th century, Darwin's warm pond became a framework, a question that could finally be explored in the language of chemistry and physics. The early Earth was unlike the blue marble we know today. Around 4.4 billion years ago, after the giant impact that formed the Moon, the planet's surface remained molten for millions of years before cooling into crust. Volcanoes exhaled carbon dioxide, methane, and ammonia, forming a dense, reducing atmosphere rich in reactive gases. Water vapor condensed into torrential rains that filled the first oceans, turning the basaltic crust into chemical soup. Lightning flashed through the thick air. Ultraviolet light from a young, unshielded sun bombarded the surface. Meteorites rained from the sky, delivering extraterrestrial carbon and organics. Energy, matter, and chaos converged. These were not the conditions for life, but for its chemistry. The primordial ocean soon became a vast reaction chamber. Its surface mixed dissolved minerals with atmospheric gases, while hydrothermal vents at the seafloor infused the waters with heat and metals. Every shoreline and tidal pool became a boundary between worlds, land and sea, solid and liquid, where molecules could concentrate, evaporate, and reform. The key challenge for life's origin was not merely the synthesis of organic compounds, but their assembly into systems, the transition from random chemistry to organized complexity. For this to occur, simple building blocks had to form, accumulate, and interact in cycles sustained by the environment. Meteorites and comets contributed crucial ingredients. Studies of carbonaceous chondrites, such as the Murchison meteorite, which fell in Australia in 1969, reveal amino acids, sugars, nucleobases, and lipids. Over 70 distinct organic compounds that mirror those found in life. These molecules likely formed in interstellar space, irradiated by cosmic rays and starlight, then delivered to young planets during the heavy bombardment period. The same rain of debris that cratered the Moon may have seeded Earth's surface with the chemistry of life. Even today, micrometeorites continue this quiet exchange, delivering tons of carbon-rich dust to the planet each year. The line between cosmic and terrestrial chemistry thus blurs. Life's first ingredients were written in the stars, long before they gathered into cells. Yet the Earth was not a passive recipient of extraterrestrial gifts. Its own internal energies, geothermal heat, lightning, and ultraviolet radiation, drove reactions that turned simple gases into complex molecules. In shallow pools, evaporation concentrated solutes. On volcanic plains, periodic drying cycles forced polymers to assemble. Near hydrothermal vents, mineral catalysts such as iron sulfide and clays fostered electron exchanges essential to organic synthesis. Across the planet, countless experiments occurred simultaneously, each testing a different configuration of atoms and energy. Life's emergence was not a single event, but a prolonged improvisation between planet and chemistry. The notion of prebiotic oceans extends Darwin's warm pond to planetary scale. In these oceans, organic molecules circulated globally, transported by currents and storms. Lightning and ultraviolet radiation continuously supplied energy, driving the formation of amino acids and sugars from atmospheric gases. Over millions of years, this steady input may have filled the oceans with a thin, organic haze, a broth of molecules floating between randomness and order. Within it, molecules competed and recombined, forming self-sustaining networks that gradually approached the threshold of metabolism. The stage was set for the first proto-biological systems. But where exactly did life take its first steps? In shallow ponds or deep-sea vents, in sunlit pools or subterranean cracks. Modern research suggests it may have arisen in multiple environments, converging upon similar solutions. Shallow ponds and tidal flats offered cycles of wetting and drying that concentrated molecules, favoring the formation of polymers like RNA and peptides. Deep-sea hydrothermal systems provided constant energy gradients and mineral catalysts. Even ice-covered oceans, once thought too cold, could protect fragile molecules from ultraviolet radiation, while concentrating solutes in thin films between ice crystals. Each environment offered its own laboratory, and nature may have used them all. The chemistry of the early atmosphere was critical. Early models suggested a strongly reducing mixture, rich in methane and ammonia, but more recent studies propose a moderately reducing composition dominated by carbon dioxide, nitrogen, and water vapor. Though less reactive, this atmosphere still produced organics when energized by lightning or ultraviolet light. The balance between volcanic outgassing, photochemistry, and impacts would have determined the abundance of prebiotic molecules reaching the surface. Crucially, the absence of oxygen preserved these compounds from oxidation. The early Earth was chemically free, a world of possibilities unrestrained by modern biochemistry. Geological evidence hints that life emerged astonishingly early. Carbon isotopic ratios in rocks from Western Australia and Greenland suggest biological activity as far back as 3.8 billion years ago, only a few 100 million years after the planet's crust solidified. This rapid appearance implies that once conditions stabilized, life may have been inevitable. The chemistry of the planet, given energy and time, seems predisposed to organize itself. The transition from non-living to living was not a miracle, but a process, slow, complex, and yet astonishingly robust. The Earth's prebiotic environment thus represents a grand convergence of cosmic and planetary chemistry. The carbon atoms forged in ancient stars found their way into comets and meteorites, then into the oceans, where heat and lightning transformed them further. The planet became a crucible, mixing celestial inheritance with geological vigor. In this view, life did not begin in isolation, but as part of a continuum that stretches from the formation of the universe itself. We are, in the most literal sense, the descendants of stardust, organized by the patient alchemy of time. The transition from chemistry to biology remains one of science's deepest mysteries, but the foundations are now visible. The early Earth provided the conditions, energy, and raw materials. The universe supplied the elements and initial organics. What followed was a sequence of chemical innovations: polymerization, replication, metabolism, each building upon the last. The warm little ponds were not mere poetic imagery. They were the microcosms where nature rehearsed the principles of life. The prebiotic oceans were the chorus that carried those experiments across the world, ensuring that somewhere, under the right balance of sunlight and chemistry, matter crossed the threshold into meaning. The story of life's origin, then, begins not with a single spark, but with a planet in conversation with its cosmos. In the dialogue between ocean and sky, energy and matter, the first molecules of inheritance were born. They would soon learn to copy themselves, to adapt, to evolve. But in the beginning, there was only chemistry, warmed by sunlight and stirred by storms. From that restless sea of possibility, life arose quietly, without design or witness, yet destined to transform the face of the world. Oparin and Haldane and the birth of chemical evolution. The early 20th century was a turning point in humanity's quest to understand its origins. The age of myth had given way to the age of mechanism, yet one mystery remained untamed: the leap from chemistry to biology. How had inert matter assembled itself into the living cell? For centuries, this question straddled the boundary between science and philosophy. The vitalists insisted that a special life force animated living things, beyond the reach of chemistry. But the rise of molecular biology, thermodynamics, and organic chemistry hinted at a different answer: that life, like stars and storms, was the product of natural law. It was in this fertile intellectual climate that two minds, working independently and on opposite sides of the world, framed a bold new idea: chemical evolution. In the 1920s, the Russian biochemist Alexander Ivanovich Oparin and the British biologist J.B.S. Haldane each proposed that life arose gradually from non-living matter through a sequence of chemical transformations. Their vision replaced spontaneous generation, the ancient belief that life could appear instantly from decay, with a patient, cumulative process. They argued that Earth's early atmosphere, lacking oxygen and rich in hydrogen, methane, ammonia, and water vapor, provided the ideal environment for organic synthesis. Energy from sunlight, lightning, and volcanic heat would drive reactions, forming increasingly complex molecules. Over time, these molecules would aggregate, self-organize, and eventually give rise to primitive cells. Life, in their model, was not a miracle, but an inevitable consequence of physics and chemistry. Oparin's path to this insight was shaped by both science and revolution. Born in 1894 in Uglitch, Russia, he grew up during an era when biology was still divided between vitalists and mechanists. Influenced by the work of the great biochemist Alexei Bach, Oparin rejected mystical explanations. He envisioned life as a continuum of chemical complexity, not a sudden appearance. In his 1924 book, The Origin of Life, he proposed that the early Earth's reducing atmosphere allowed organic molecules to accumulate without being destroyed by oxidation. These molecules, he suggested, concentrated in the oceans and formed microscopic droplets, cosovates, that exhibited primitive lifelike properties such as metabolism, growth, and division. Though not alive in the biological sense, these cosovates could evolve chemically, setting the stage for true cells. Oparin's theory was revolutionary. It introduced the idea that self-organization could arise naturally from molecular interactions. his conjugates, mixtures of proteins, lipids, and other molecules suspended in water, formed spontaneously in the laboratory and exhibited behaviors startlingly similar to living cells. They absorbed nutrients, grew, and sometimes divided into smaller droplets. To Oparin, these were the precursors of life, transitional forms, bridging chemistry and biology. His work shifted the question from who created life to how did chemistry organize itself into life. In doing so, he planted the seed for a new science, the study of abiogenesis as a natural process. Meanwhile, across Europe, J.B.S. Haldane, a brilliant eccentric polymath, was reaching similar conclusions. Born into an aristocratic Scottish family in 1892, Haldane combined the instincts of a philosopher with the rigor of a geneticist. His background in evolutionary biology gave him a unique perspective. If species could evolve by natural selection, why not molecules? In a 1929 essay titled The Origin of Life, Haldane proposed that Earth's primitive atmosphere lacked oxygen and was thus a reducing environment. In such conditions, ultraviolet radiation from the sun would provide energy for the synthesis of organic compounds. Over time, he suggested, the oceans would become a hot dilute soup of amino acids, sugars, and nucleotides, the raw materials of life. Eventually, some of these compounds would form systems capable of replication and metabolism. In essence, Haldane envisioned evolution, beginning at the molecular level, chemical evolution preceding biological evolution. The intellectual parallel between Oparin and Haldane was striking, though they developed their ideas independently. Both rejected the notion of a spark of life, replacing it with a gradual process governed by physical laws. Both recognized the importance of Earth's early atmosphere, devoid of oxygen, but rich in energy. And both foresaw that life's emergence required not only the synthesis of organic molecules, but their organization into self-sustaining systems. What differed were the metaphors. Oparin's co-servates versus Haldane's primordial soup. Yet the underlying idea that complexity could emerge naturally from simplicity united them. It was the birth of a new paradigm. This concept of chemical evolution resonated deeply with the broader intellectual movements of the early 20th century. Physics had revealed that order could arise spontaneously from chaos, as in the crystallization of solids or the organization of galaxies from cosmic gas. Thermodynamics showed that open systems could maintain structure by dissipating energy. In chemistry, researchers had synthesized organic molecules from inorganic precursors, undermining the old vitalist distinction. Oparin and Haldane extended these insights into biology. If molecules could self-assemble into crystals, perhaps they could also self-organize into cells. The boundary between life and non-life, they suggested, might not be a wall, but a gradient. The power of their theories lay not only in their vision, but in their testability. By grounding life's origin in chemistry, Oparin and Haldane invited experimental investigation. If organic molecules could form naturally, perhaps their synthesis could be replicated in the laboratory. This invitation would soon be answered, 3 decades later, by Stanley Miller and Miller-Urey, whose 1953 experiment electrified science. But even before that landmark, the Oparin-Haldane model had reshaped the philosophical landscape. Life was no longer an exception to nature's laws. It was an expression of them. Oparin's co-servate model, though ultimately supplanted by more detailed biochemical theories, remains conceptually profound. It captured the essential idea of compartmentalization, that life requires boundaries to maintain organization. Modern research on protocells, lipid vesicles, and micelles echoes his insight. Similarly, Haldane's vision of a hot dilute soup anticipated the modern understanding of prebiotic chemistry as a global phenomenon, influenced by atmosphere, ocean, and energy flux. Both men understood that life's emergence was not a localized accident, but a planetary process, chemistry unfolding across continents and epochs. The term chemical evolution, which entered the scientific lexicon in the 1930s, encapsulated this idea beautifully. Just as Darwin's biological evolution described the diversification of species through natural selection, chemical evolution described the gradual increase in molecular complexity through natural processes. Simple molecules combined into polymers. Polymers interacted to form networks. Networks gave rise to metabolism and replication. At each stage, feedback and stability guided progression toward higher organization. The analogy to biological evolution was not literal. Molecules do not compete in the Darwinian sense, but metaphorical. Both processes involve selection, persistence, and adaptation to energetic constraints. The political and philosophical environments in which Oparin and Haldane worked also shaped their interpretations. Oparin, living in the Soviet Union, framed his theory in materialist terms, aligned with Marxist philosophy, emphasizing dialectical transformation from quantity to quality. Haldane, a Marxist sympathizer himself, viewed life's emergence as an inevitable outcome of physical law, not divine intervention. Their alignment, though ideological as well as scientific, underscored a deeper conviction that the universe is self-organizing, creative, and sufficient unto itself. In this sense, chemical evolution became not just a scientific model, but a worldview, a declaration that life is a natural consequence of matter becoming aware. The legacy of Oparin and Haldane endures in every modern study of abiogenesis. Their vision laid the foundation for prebiotic chemistry, for experiments in molecular self-assembly, for models of protocell formation and metabolic networks. They introduced the principle that the origin of life is a continuum, not a leap, a transformation governed by thermodynamics and time. And perhaps most importantly, they transformed an ancient question into a scientific pursuit. Before them, how did life begin? Belonged to theology. After them, it belonged to chemistry. Looking back, one can see how prescient their insights were. The coextravates that Oparin described now find their analogues in lipid vesicles, the membrane bubbles that can enclose RNA and proteins. The chemical cycles Haldane imagined now appear in models of autocatalytic networks that sustain themselves through feedback. The primordial soup he described has been found not only in early Earth analogues, but in the atmospheres of other planets and moons. Titan, for instance, with its methane rain and complex hydrocarbons, resembles Haldane's vision, a world suspended between chemistry and life. In the end, the significance of Oparin and Haldane lies not in the precision of their details, but in the power of their principle, that life is the outcome of gradual transformation, not sudden creation. Their work bridged the chasm between geology and biology, showing that the same laws that govern stars and stones also govern cells. It is a profoundly unifying idea, that the universe is continuous in its creativity, that from the cooling of planets to the firing of neurons, there is one unfolding story of matter organizing itself. In that story, the birth of life on Earth is not an isolated miracle, but a chapter in the grand narrative of chemical evolution. The Miller-Urey experiment and its legacy. In the spring of 1953, inside a small laboratory at the University of Chicago, the ancient question of life's origin was distilled into glassware and electricity. Two men, a graduate student named Stanley Miller and his mentor, Harold Urey, a Nobel Prize-winning chemist, had decided to recreate the chemistry of the early Earth in miniature. Their goal was audacious: to test whether the molecules of life could arise spontaneously from simple gases and energy, as Oparin and Haldane had proposed decades earlier. The apparatus they built was simple, elegant, and destined to change the course of science. It consisted of a closed-glass system containing two main chambers. In one, water was boiled continuously to simulate the primitive ocean. In the other, a mixture of gases, methane, CH4, ammonia, NH3, hydrogen, H2, and water vapor, H2O, represented the atmosphere. Electrodes delivered sparks through the gas mixture, mimicking lightning storms thought to have raged across the early Earth. The vapors cycled through the system. Water evaporated, mixed with gases, condensed, and dripped back into the ocean flask. For days, this artificial world churned under continuous energy input, an echo of the restless planet billions of years ago. After a week, the clear liquid in the apparatus had turned a murky reddish-brown. When Miller analyzed it, he discovered something extraordinary. Within that fluid were amino acids, the fundamental building blocks of proteins. Glycine, alanine, and several others had formed spontaneously from simple inorganic gases. Life's chemistry had emerged from non-living matter without any guiding hand. It was the first empirical demonstration that organic molecules could arise through natural processes. In a single stroke, Miller and Urey had transformed the origin of life from philosophical speculation into experimental science. The scientific world erupted in astonishment. Newspapers proclaimed that life has been created in a test tube, though Miller himself was careful to clarify that no living cells had formed, only organic compounds. Nevertheless, the implications were profound. The experiment provided direct evidence supporting the Oparin Haldane hypothesis. Given a reducing atmosphere, energy, and water, the precursors of life could form readily. Chemistry alone could take the first steps toward biology. To appreciate the significance of this breakthrough, one must consider its historical context. At the time, molecular biology was just emerging. The structure of DNA was being deciphered by Watson and Crick that very same year, 1953. The idea that life's complexity could arise from chemistry seemed to many improbable. Vitalism had only recently lost its grip, and the gap between inorganic and organic still appeared vast. Miller and Urey's apparatus bridged that gap. In its glass coils, electricity and gas became molecules that, given time and evolution, might have become cells. The origin of life was no longer a mystery of divine creation, but a puzzle of physics and chemistry. The mechanism behind the experiment's success lay in the simplicity of its ingredients. The chosen gases were reducing, rich in hydrogen, which facilitates the formation of carbon-hydrogen and carbon-nitrogen bonds, essential for organic molecules. The electrical discharges provided the energy to break molecular bonds and drive recombination. Hydrogen cyanide and formaldehyde, transient intermediates in the reactions, polymerized into amino acids and other compounds. Over time, these molecules accumulated in the water phase, just as they might have accumulated in Earth's primordial oceans. The system, though primitive, recreated the basic thermodynamic conditions of early Earth. Energy flow through a mixture of simple molecules leading to chemical complexity. Miller's results ignited a wave of similar experiments worldwide. Researchers modified the atmospheric composition, energy sources, and environmental parameters to test the robustness of abiotic synthesis. Ultraviolet lamps replaced lightning. Shock waves mimicked meteor impacts. Hot mineral surfaces stood in for volcanic plains. In nearly every case, organic molecules formed. Not only amino acids, but sugars, lipids, nucleobases, and even short polymers resembling peptides and nucleotides. The message was clear. organic synthesis is inevitable under a broad range of plausible planetary conditions. Nature, when supplied with energy and the right ingredients, produces complexity as readily as stars produce light. But as science progressed, the simplicity of Miller and Urey's atmosphere came into question. Geological evidence suggested that the early Earth's air may have been less reducing and more neutral, dominated by carbon dioxide, CO2, nitrogen, N2, and water vapor. Such an atmosphere is less favorable for amino acid synthesis. However, later experiments showed that even under these neutral conditions, organic compounds can still form, especially if other energy sources such as ultraviolet light, cosmic rays, or impact shocks are included. Moreover, local environments, like volcanic plumes or hydrothermal vents, could have maintained pockets of reducing gases. The early Earth was chemically diverse. Miller's model represented one of many plausible microenvironments. His experiment captured the principle, not the full complexity. In 2008, decades after Miller's death, a reanalysis of his original samples using modern techniques revealed that his apparatus had produced over 20 different amino acids, far more than initially detected. This discovery reaffirmed the robustness of his results and extended their significance. Life's molecular alphabet, it seemed, could indeed be written by lightning in a primordial sky. Even as scientific details evolved, the central truth remained. The building blocks of life arise naturally under geochemical conditions. The legacy of the Miller-Urey experiment reaches far beyond its immediate findings. It established a new methodology, the simulation of planetary environments as a way to explore prebiotic chemistry. From that point onward, the origin of life became an experimental science. Researchers began constructing ever more sophisticated models of early Earth. Hydrothermal reactors simulating seafloor vents, high-pressure cells replicating volcanic eruptions, photochemical chambers reproducing interstellar conditions. Each experiment extended Miller's insight. That complexity emerges when energy flows through matter. The experiment also inspired a new field, astrobiology. If life's building blocks can form easily on Earth, they can form elsewhere. Indeed, the same organic molecules have since been found in meteorites, comets, and interstellar clouds, confirming that prebiotic chemistry is a universal process. The Miller-Urey apparatus, though small and terrestrial, had cosmic implications. It demonstrated that the fundamental chemistry of life is not unique to Earth, but woven into the fabric of the universe. Still, the experiment had limitations. It created monomers, simple molecules, but not the polymers or self-replicating systems that define life. The gap between amino acids and proteins, between nucleobases and genes, remained immense. Yet, the conceptual leap had been made. The challenge shifted from synthesis to organization. How could these molecules assemble into self-sustaining networks? In this way, Miller and Urey's work set the stage for subsequent explorations. The RNA world, metabolism-first theories, and protocell models that would follow. Their experiment was not the answer, but the beginning of a new question. Philosophically, the experiment carried a quiet but profound message. It suggested that life is not a rare miracle, but the natural outcome of universal laws. The same physics that governs stars and storms also governs chemistry's ascent toward biology. In the glass sphere of Miller's apparatus, humanity glimpsed a miniature cosmos, one driven by energy, chance, and time. It was a symbolic moment in science, the first demonstration that the seeds of life could be sown by lightning and gas, without divine intervention, guided only by the deep symmetry of natural law. Miller himself remained modest about his achievement. "We did not create life," he often said. "We created the conditions under which life could begin." Yet that modesty conceals the magnitude of his contribution. His experiment was the Rosetta Stone of abiogenesis, the translation of theory into tangible chemistry. Every subsequent model, from hydrothermal vents to extraterrestrial panspermia, traces its lineage to that glass apparatus humming in Chicago in 1953. In the decades since, new discoveries have enriched the story. Laboratory simulations using more complex environments, volcanic gases, mineral catalysts, and cyclic temperature changes, have generated peptides and nucleotides spontaneously. Meteorite analyses have confirmed that amino acids identical to those in Miller's experiment form naturally in space. The European Space Agency's Rosetta mission detected glycine and phosphorus on Comet 67P, proving that prebiotic chemistry occurs on cosmic scales. The distinction between terrestrial and extraterrestrial synthesis has blurred. The universe itself appears to be a prebiotic laboratory. Modern versions of Miller's setup now employ advanced spectrometry, automated sampling, and computational modeling to track reaction pathways in real time. These experiments reveal a rich, self-organizing chemical network that evolves toward increasing complexity, a dynamic mirror of the early Earth's geochemical cycles. What Miller achieved with glass and spark gaps has become a discipline in itself. Systems chemistry, the study of how molecular ensembles give rise to emergent properties. In this sense, his experiment remains alive, not as a historical relic, but as a continuing inquiry into how matter learns to organize itself. The Miller-Urey experiment also carries a symbolic resonance beyond science. It captures a moment when human curiosity, distilled into an experiment, reached backward in time to witness the dawn of its own existence. Within those flasks, 1 billion years of planetary history played out in miniature. The lightning of creation, the chemistry of potential, the transformation of inert gas into the scaffolding of life. It was both an act of replication and reverence, a reminder that the boundary between living and non-living is one of degree, not kind. In the grand story of the cosmos, Miller's sparks echo the first storms that flashed over Earth's ancient seas. They reveal a truth both humbling and profound, that the ingredients of life are not rare or fragile, but inevitable, wherever energy and chemistry conspire. The experiment's brownish residue, once regarded as mere sludge, is, in a sense, the handwriting of the universe. It is the first signature of life's intention, drawn in carbon and lightning, waiting for time to translate chemistry into consciousness. RNA world and alternative origin pathways. If the Miller-Urey experiment revealed that the building blocks of life could form spontaneously, the next great question was how those molecules learned to copy themselves. Life, after all, is defined not merely by chemistry, but by information. The ability to store, transmit, and reproduce patterns. Somewhere between amino acids and organisms, chemistry began to remember. Out of that memory arose the first genetic systems, and with them, evolution itself. To understand how lifeless molecules crossed that threshold, scientists turned their attention to one remarkable molecule, RNA, the ribonucleic acid that today carries the genetic and catalytic essence of life. In every cell, DNA holds the instructions of life, but it does nothing on its own. It must be read, copied, and translated by enzymes, proteins that themselves are encoded by DNA. This interdependence creates a paradox known as the chicken and egg problem of molecular biology. DNA requires proteins to function, and proteins require DNA to be produced. How then could either have existed first? The resolution to this riddle came in the 1960s and 70s, with the discovery that RNA, a close cousin of DNA, can act as both. a carrier of information, and a catalyst capable of driving chemical reactions. This dual nature suggested that before DNA and proteins, there was an RNA world, a primordial stage of evolution dominated by self-replicating RNA molecules. The idea of the RNA world was first articulated by scientists such as Carl Woese, Leslie Orgel, and Francis Crick in the late 1960s. They proposed that early life used RNA both to encode genetic information and to perform catalytic functions necessary for replication. Unlike DNA, RNA's single-stranded structure allows it to fold into complex shapes that can catalyze reactions, much like enzymes. The discovery of such catalytic RNAs, ribozymes, in the 1980s by Thomas Seck and Sidney Altman, provided experimental proof. Ribozymes could cut and rejoin RNA strands, catalyze peptide bond formation, and even replicate short sequences. Suddenly, the idea that life began with RNA was no longer speculative. It had molecular support. The RNA world hypothesis envisions a planet rich in nucleotides, the building blocks of RNA, formed through prebiotic chemistry. These nucleotides polymerized spontaneously, perhaps on clay minerals that concentrated and aligned them, forming chains capable of storing information. Once a strand could copy itself, even imperfectly, evolution began. Replication introduced variation. Variation invited selection. Molecules that replicated more efficiently or resisted degradation would dominate, setting off a chemical evolution that eventually led to the genetic systems we know today. In this view, life began not with cells, but with molecules engaged in a struggle for persistence. Yet the path from simple chemistry to the first replicating RNA is anything but straightforward. Nucleotides are complex molecules requiring precise conditions for synthesis. They consist of three parts: a sugar, ribose, a phosphate group, and a nitrogenous base, each formed through different chemical routes. The challenge of assembling them in the same environment led some to doubt whether RNA could have arisen spontaneously. Nevertheless, experimental breakthroughs in the early 21st century have shown plausible pathways. Chemists like John Sutherland demonstrated that nucleotides could form from simple precursors, such as hydrogen cyanide and formaldehyde, under ultraviolet light, the same conditions prevalent on early Earth. These reactions produce ribonucleotides in yields sufficient to seed an emerging RNA world. Nature, it seems, had multiple routes to the same destination. Once RNA existed, the next step was self-replication. Laboratory experiments have produced short ribozymes capable of copying pieces of RNA, though not yet entire genomes. The principle, however, is clear. RNA. Molecules can act as both template and catalyst, closing the loop between information and chemistry. Some modern viruses, such as retroviruses, still rely solely on RNA for their genetic material, living relics of this earlier epoch. Ribosomes, the protein factories of all cells, are themselves ribozymes at heart. Their catalytic core is RNA, not protein. Every living organism carries within its cells a molecular fossil, the memory of an ancient RNA-dominated world. The RNA world concept offers a unifying framework for the emergence of life's essential functions: replication, mutation, and selection. It bridges chemistry and Darwinian evolution in a single step. Yet it also opens deeper questions. If RNA came first, what came before RNA? The synthesis of nucleotides still requires relatively advanced chemistry. Some researchers propose a pre-RNA world in which simpler polymers, such as peptide nucleic acids, PNA, or threose nucleic acids, TNA, preceded RNA, providing the structural and chemical stepping stones. These molecules can store information and form base pairs, but are easier to synthesize under prebiotic conditions. Once RNA arose, it may have replaced these earlier systems because of its greater versatility and stability, establishing itself as the molecular monarch of early life. Parallel to this genetic model, other scientists emphasize a different starting point: metabolism first hypotheses. In these scenarios, networks of chemical reactions, not informational polymers, came first. Life began as a set of self-sustaining chemical cycles powered by environmental energy gradients, such as those found near hydrothermal vents. Over time, these reaction networks grew more complex and incorporated informational molecules like RNA. The RNA world and metabolism first views are not mutually exclusive. They may describe consecutive stages in life's emergence, chemistry learning to store information only after learning to sustain itself. Still others explore the possibility that life's earliest replicators combined both approaches, hybrid systems in which short peptides and RNA molecules co-evolved, reinforcing each other's functions. Experiments show that small peptides can stabilize RNA structures and enhance their catalytic activity. Likewise, RNA can catalyze peptide bond formation. This synergy suggests that life's earliest systems were not purely RNA-based, but involved a dance between nucleic acids and proteins, a proto-life consortium from which the genetic code itself eventually arose. The boundary between the RNA world and the first cells may thus be a continuum, not a sudden transition. A major puzzle in all these models is the problem of homochirality, the fact that biological molecules like amino acids and sugars exist in only one of two possible mirror image forms. Prebiotic chemistry produces both left and right-handed versions equally. How did life choose one over the other? Some researchers suggest that polarized light from the early sun, magnetic fields, or even asymmetric mineral surfaces could have broken the symmetry. Once a bias appeared, self-replicating molecules would have amplified it. Chirality, like replication, may have emerged through feedback, an inevitable consequence of self-organization in a nonlinear system. Modern research has expanded the RNA world idea into the broader concept of the RNA protein continuum. In this model, RNA served as the template and catalyst for protein synthesis, while peptides stabilized RNA and expanded its catalytic repertoire. Over time, the division of labor we see today, DNA for storage, RNA for translation, proteins for function, evolved from a unified ancestral chemistry. The genetic code itself may have begun as a loose association between specific RNA sequences and amino acids, later refined by selection into the precise correspondence used by all life. In this light, the RNA world is not a discrete epoch, but a bridge between the inorganic and the biological, between random polymerization and structured heredity. One of the most remarkable aspects of the RNA world hypothesis is its universality. It predicts that wherever life emerges, on Earth, Mars, or distant exoplanets, it will likely pass through a similar stage, a world of self-replicating polymers, capable of both storing and processing information. The specific chemistry might differ, perhaps based on alternative backbones or solvents, but the logic will remain the same. Life, in this view, is the natural outcome of the universe learning to encode memory. The RNA molecule becomes not merely a biological artifact, but a cosmic archetype, the pattern by which matter becomes aware of its own continuity. Despite its elegance, the RNA world remains an incomplete story. No laboratory has yet produced a fully self-replicating RNA system from scratch, capable of Darwinian evolution without intervention. The synthesis of long RNA chains under prebiotic conditions remains challenging, and the stability of RNA in early Earth's harsh environment is uncertain. Nevertheless, progress continues. Recent experiments have shown that simple environmental cycles, drying and rehydration, freezing and thawing, can drive polymerization and strand separation, mimicking natural replication cycles. In miniature, we glimpse how the early planet could have been a vast laboratory of repeating chemical experiments, each one edging closer to life. The RNA world stands as one of the most beautiful ideas in modern science because it unites simplicity and power. A single molecule, humble, unstable, but versatile, may have bridged the chasm between non-living chemistry and living biology. It encodes not only information but possibility. In its elegant loops and folds lies the script from which all future complexity was read. From the first ribozyme to the human genome, the thread of continuity is unbroken. We are, in a profound sense, the descendants of that first strand, a molecule that learned to copy itself, and in doing so, began to dream. In the end, whether life began in an RNA world, a metabolic network, or some hybrid of the two, the principle remains the same. Organization emerges from interaction. Energy flows through matter, feedback shapes complexity, and stability selects persistence. The origin of life is not a miracle of chance, but the inevitable outcome of a universe that evolves structure wherever energy and chemistry meet. RNA was simply the first language of that conversation, a syntax of atoms that allowed matter to speak itself into living form. Metabolism. First and hydrothermal vent. Hypotheses. If the RNA world theory imagines life's origin as the triumph of information, molecules learning to copy themselves, the metabolism first hypothesis offers a different vision. Life began not with code, but with cycles of chemistry. Before the first genes or enzymes, before even RNA, there may have existed a self-sustaining web of reactions, a planetary metabolism driven by the Earth's heat and minerals. In this picture, life did not begin with molecules whispering, "Copy me," but with matter learning to flow, transform, and renew. The spark of life was not replication, but continuity. The metabolism first idea arises from a profound question. Can chemistry organize itself without genetic templates? In biology, metabolism is the network of chemical reactions that converts energy and matter into the components of cells. Yet even without life, the planet's surface teems with energy gradients, from volcanic heat and sunlight to chemical disequilibria between ocean and crust. These gradients naturally drive reactions, assembling and breaking molecules in cycles. If such cycles could close upon themselves, recycling intermediates and generating complexity, they would form the basis of a primitive, pre-genetic metabolism, a living chemistry before living cells. The geochemical context for this hypothesis lies in one of Earth's most enigmatic environments, the hydrothermal vents of the deep ocean. Discovered in 1977 along the Galapagos Rift, these black smokers and alkaline vents revealed ecosystems thriving in total darkness, powered not by sunlight, but by chemistry. Sulfide-rich fluids, heated by magma, rise from the seafloor and mix with cold seawater, creating sharp gradients in temperature and chemistry. Microbes in these environments live on energy extracted from reactions between hydrogen, carbon dioxide, and sulfur, the very same ingredients abundant on the early Earth. To many scientists, these vents are more than ecological curiosities. They are windows into the planet's primeval laboratory. Among the most compelling models inspired by this environment is the iron-sulfur world hypothesis, proposed by German chemist Günther Wächtershäuser in the 1980s. He envisioned life beginning on the surfaces of iron and nickel sulfide minerals at hydrothermal vents. These metallic surfaces, rich in catalytic power, could facilitate reactions between carbon dioxide and hydrogen to form organic molecules such as acetic acid, a fundamental metabolite in modern cells. The key insight was that these reactions could be autocatalytic, forming networks that produce their own catalysts. As intermediates accumulated, cycles could self-reinforce, eventually giving rise to primitive metabolic pathways resembling the modern Krebs cycle, the universal core of cellular energy metabolism. In Wechtershäuser's view, the earliest life forms were not free-floating molecules, but surface-bound metabolic systems, thin films of reactions adhering to mineral surfaces, sustained by the continuous flow of energy from the vent. Over time, these networks became more complex, forming compartments and membranes that eventually detached to become protocells. The environment provided everything needed: gradients of pH and temperature, catalytic minerals, and a steady energy supply. Life, he argued, was not a rare accident, but an inevitable geological process, an extension of the Earth's own metabolism. Later research expanded this vision. British biochemist Nick Lane and geologist Michael Russell proposed the alkaline hydrothermal vent model, focusing on a gentler class of vents, such as those found at the Lost City site in the mid-Atlantic. Unlike the acidic black smokers, these vents emit warm, alkaline fluids rich in hydrogen and methane. As the alkaline fluids mix with slightly acidic seawater, they form natural microporous structures composed of minerals like iron nickel sulfides and clays. These structures resemble honeycombs, with millions of tiny compartments separated by thin mineral walls, only microns thick. Each compartment maintains a natural electrochemical gradient, a difference in pH and electrical potential across the wall, much like the proton gradients that power modern cells through ATP synthesis. Russell and Lane proposed that these mineral pores acted as natural protocells, providing the compartmentalization and energy gradients needed for metabolism. Carbon dioxide from seawater, reacting with hydrogen from the vent fluid, could be reduced to form simple organic compounds, such as formate, acetate, and methane. These reactions are thermodynamically favorable in the presence of catalytic metals. The compartments, meanwhile, trapped and concentrated products, preventing their diffusion into the ocean. Over time, such systems could evolve increasing complexity, coupling chemical cycles, synthesizing cofactors, and eventually incorporating genetic polymers like RNA. The transition from geochemistry to biochemistry would have been continuous, not abrupt. Life, in this scenario, was born in the flow of energy across a membrane, just as it remains today. The beauty of the hydrothermal vent model lies in its self-sufficiency. It solves three major problems of prebiotic chemistry: concentration, catalysis, and energy. First, concentration. Because the microscopic pores of vent structures act as natural reaction vessels, preventing dilution. Second, catalysis. Because metal sulfides such as iron sulfide and nickel sulfide can facilitate electron transfers essential to carbon fixation. And third, energy. Because the vent's chemical disequilibrium provides a constant supply of free energy, sustaining the reactions indefinitely. In effect, hydrothermal systems create a natural battery, a continuous source of power that can drive molecular evolution. Life, it seems, may have begun not in the open sea, but within the stone labyrinths of the deep. The metabolic approach also offers an elegant continuity with modern biology. Every living cell today relies on proton gradients across membranes to generate ATP, the universal energy currency. The enzymes that perform this, ATP syntheses, are molecular turbines, rotating as protons flow across membranes. The similarity between these biological proton gradients and the natural gradients in alkaline vents is striking. It suggests that life did not invent its energy system from scratch, but inherited it from the planet itself. The first cells were, in essence, mineral reactors that learned to close themselves off from their geological womb. The metabolism first hypothesis also redefines what life means. Instead of focusing on replication or genetics, it emphasizes organization and flux, the dynamic maintenance of order through energy flow. In this view, life is not an object, but a process, a self-sustaining pattern of reactions maintained far from equilibrium. The physicist Erwin Schrödinger, in his 1944 essay, What is Life?, described organisms as systems that feed on negative entropy, maintaining order by exporting disorder to their surroundings. Hydrothermal systems fit this definition perfectly. They are engines of order, converting geochemical energy into structure. If given time and the right conditions, such order could stabilize, adapt, and evolve. Critics of the metabolism-first model argue that, without genetic information, chemical cycles lack heredity, the capacity to improve through evolution. But proponents respond that heredity can exist in networks as well as molecules. In autocatalytic systems, the relative abundance of reactants and catalysts can store and transmit information, allowing the system to reproduce its pattern. Laboratory experiments have demonstrated self-propagating chemical networks that exhibit quasi-Darwinian behavior, selection for stability and efficiency. These findings suggest that evolution itself may predate genes, that natural selection, in its most general sense, applies to any system that maintains structure through energy flow. Beyond the seafloor, the metabolism-first framework has inspired a broader search for life's precursors in other cosmic environments. The icy moons, Europa and Enceladus, both known to harbor subsurface oceans heated by tidal energy, show evidence of hydrothermal activity at their sea floors. The plumes of Enceladus, sampled by the Cassini spacecraft, contain molecular hydrogen, methane, and organic compounds, precisely the ingredients of vent chemistry. If the metabolism-first model is correct, then these moons may host active prebiotic chemistry, or even living systems independent of sunlight. The universe may thus be rich in deep ocean biospheres, hidden beneath ice, powered by the same geochemical engines that once animated Earth's first cells. The vent model also connects beautifully with the later emergence of genetic systems. Once primitive metabolic networks existed, they could have provided the stability and energy needed for informational molecules like RNA to arise. The porous mineral walls of vents may have served as both catalytic scaffolds and protective niches, enabling the formation of nucleotides and their polymerization. In this sense, the metabolism first and RNA world hypotheses are complementary, not competing. The first established the environment of flow and energy. The second introduced memory and inheritance. Together, they describe the dual birth of life. Chemistry first learning to sustain, then to remember. What makes the hydrothermal vent narrative so compelling is its symmetry with the world we see today. The last universal common ancestor, LUCA, inferred from comparative genomics, appears to have lived in a hot, chemically rich, anaerobic environment, precisely like a hydrothermal vent. LUCA's enzymes use metal cofactors similar to those found in vent minerals, and its metabolic pathways mirror geochemical cycles. In a profound sense, we have never truly left the vents. Every cell is a continuation of their chemistry, still powered by gradients and metals, still thriving between heat and water. The image of life's origin at the seafloor is almost mythic in its grandeur. In the black silence of the Hadean Ocean, energy rose from the planet's heart, meeting the cooling waters of the sky. Between those two worlds, fire and sea, chemistry awakened. Minerals served as both cradle and teacher. Gradients became the rhythm of metabolism, and in that eternal darkness, matter found a way to persist. Long before eyes or sunlight, there was lightless life, born in the interplay of stone, water, and heat. It is a vision both humbling and unifying. Life as the inevitable flowering of a restless planet. In the end, whether life began in a warm pond or a hydrothermal vent, whether its first step was information or metabolism, all paths lead to the same truth. The Earth itself was alive long before it gave birth to organisms. Its rocks catalyzed reactions. Its oceans cycled molecules. Its atmosphere shared energy with the sun. The planet was a vast experiment in self-organization, and we are its result. To understand the metabolism, first hypothesis is to see life not as an anomaly, but as continuity, the extension of planetary chemistry into biology. The vent, the cell, and the cosmos all share the same principle. Energy flowing through structure, giving rise to form. Life, in the deepest sense, is the universe learning to metabolize itself. The emergence of protocells and molecular selection. At some point in the long evolution from lifeless matter to living systems, chemistry became enclosed, separated from the world by a thin, trembling film. That moment, when the first membranes formed, marks the birth of individuality in the cosmos. Until then, molecules reacted freely in oceans and vents, in ponds and clays, dissolving into the planetary whole. But with the advent of protocells, chemistry began to draw boundaries around itself. Inside those boundaries, reactions could stabilize, concentrate, and evolve. The cell, the fundamental unit of life, was beginning to take shape. The term protocell refers to a primitive, prebiotic structure that exhibits some, but not all, of the characteristics of modern life. Compartmentalization, energy flow, chemical synthesis, and crucially, reproduction. A protocell is not alive in the biological sense, but it stands at the threshold where molecular systems begin to behave as organisms. Within its boundary, molecular networks are shielded from the vast dilution of the environment, allowing evolution to act on localized chemistry. The protocell is life's first experiment in containment, the vessel in which selection began. The building blocks of protocells are deceptively simple. Fatty acids, among the most ancient organic molecules, form spontaneously under prebiotic conditions. They can arise through reactions between carbon monoxide and hydrogen on metal catalysts, or from the photolysis of simple hydrocarbons in the atmosphere. When mixed in water, these amphiphilic molecules, possessing both hydrophilic heads and hydrophobic tails, spontaneously assemble into micelles and vesicles, hollow spheres that enclose a watery interior. This self-assembly occurs without any guiding hand, driven only by the physics of surface tension. Nature, it seems, was predisposed to build membranes. Experiments have shown that fatty acid vesicles can grow and divide under simple conditions. When additional fatty acids are added to the surrounding solution, they insert into the vesicle membrane, causing it to expand. As the vesicle elongates, it eventually pinches off into two smaller vesicles, a primitive form of replication. Unlike modern cells, these protocells lack genetic control, but they already embody the logic of life: growth, division, and inheritance by physical continuity. The first step toward biology may thus have been a purely physical process, guided by thermodynamics rather than genes. The encapsulation provided by protocells created a protected microenvironment in which chemical evolution could accelerate. Within these lipid bubbles, concentrations of nucleotides, peptides, and other small molecules could reach levels high enough for complex reactions to occur. If RNA or other catalytic molecules were trapped inside, their replication and function could proceed more efficiently than in open solution. Over time, protocells that enclosed beneficial chemistries would outcompete those that did not. This is the beginning of molecular selection, the earliest form of evolution, operating not on organisms, but on chemical assemblies. Modern laboratory experiments have recreated many of these steps. In one striking example, researchers encapsulated self-replicating RNA enzymes inside lipid vesicles. The RNAs catalyzed reactions that altered the vesicle's internal chemistry, causing those protocells to grow faster than their neighbors. When the vesicles divided, the catalytic RNA was distributed among the offspring, preserving functionality. This primitive coupling between genotype the RNA and phenotype the vesicle's behavior mirrors the essence of natural selection, differential reproduction, based on heritable variation. In miniature, life's evolutionary algorithm was already running. Theoretical models show that once such coupling exists, complexity can increase rapidly. Protocells containing cooperative networks of molecules, such as mutually reinforcing catalysts, can sustain themselves longer and divide more efficiently. Competition among protocells for limited resources would naturally select for those with more efficient internal chemistry. Even without sophisticated replication mechanisms, the feedback between internal reactions and membrane dynamics produces selection pressure. The result is evolution by physics, patterns of matter persisting because they stabilize their own conditions for existence. Another critical innovation likely occurred when protocells began to harness energy gradients. Early membranes were leaky, allowing ions and small molecules to pass freely. But gradual changes in lipid composition could have made them semi-permeable, enabling protocells to maintain internal disequilibria, the very essence of metabolism. If redox reactions or proton gradients existed inside, these systems could store and release energy, driving further chemistry. The membrane thus became not only a container, but an engine, converting environmental energy into internal organization. This mirrors what cells do today. They feed on gradients, perpetuating structure through controlled flow. Mineral surfaces may have played a key role in this transition. Protocells forming near hydrothermal vents or clays could have incorporated catalytic minerals into their membranes, enhancing chemical reactivity. Iron-sulfur clusters, for instance, can mediate electron transfers, much like the cofactors in modern enzymes. As these mineral-assisted reactions became internalized, protocells would gradually gain autonomy from their environment. The evolution of metabolism, in this view, was the process of internalizing geochemistry, bringing the planet's catalytic power inside the boundary of life. The next step was communication between protocells. When vesicles grow and divide, they can fuse with one another, exchanging contents. Such molecular recombination accelerates evolution, allowing successful chemical innovations to spread. In this communal stage of prebiotic evolution, information was not yet encoded in genes, but shared through direct material exchange, a chemical conversation across membranes. Life's first ecosystems may thus have been networks of interacting protocells, exchanging molecules, competing for energy, and collectively exploring the space of possibility. In this early world, selection did not act on single molecules, but on ensembles, integrated systems of reaction and structure. The most stable and self-reinforcing assemblies persisted, while unstable ones dissolved. This principle, known as autocatalytic set theory, has been developed mathematically by researchers like Stuart Kaufman. It shows that in sufficiently complex chemical systems, networks of mutually catalytic reactions arise spontaneously. These networks can self-replicate at the systems level, providing a theoretical basis for metabolism-first life. Encapsulation within protocells gave such networks identity and stability, allowing them to evolve as distinct entities. What we call organisms began as self-sustaining chemical networks wrapped in membranes. Over time, natural selection at the protocell level would have favored tighter coupling between internal chemistry and external structure. Protocells containing RNA or peptide catalysts that improved resource utilization would grow faster. Those that could capture environmental energy from redox reactions, light or heat, would sustain themselves longer. Eventually, a division of labor emerged. Informational molecules guided catalysis, while structural molecules maintained integrity. The first genetic systems, perhaps RNA-based, arose within this context, not in isolation, but as part of a larger metabolic ecosystem already capable of growth and competition. Life did not begin as a molecule, but as a relationship between molecules. The emergence of protocells also redefines the concept of the first cell. There was likely no single ancestral protocell that gave rise to all life, but rather a community of interacting lineages, exchanging components and evolving collectively. This communal evolution would have blurred the distinction between individual and environment. Only later, as membranes became less permeable and genetic systems more stable, did individuality sharpen. The universal ancestor, LUCA, the last universal common ancestor, was not the first cell, but the survivor of a long lineage of communal chemistry that learned to isolate itself completely. The protocell story reveals a profound unity between physics, chemistry, and biology. The processes that govern droplet formation, diffusion, and phase separation are the same that underlie life's emergence. Recent research in soft matter physics and non-equilibrium thermodynamics shows that self-organizing droplets can spontaneously develop behaviors resembling metabolism, chemical oscillations, nutrient uptake, and division, purely from reaction-diffusion dynamics. These findings blur the line between living and non-living, suggesting that life is not a discrete state, but a continuum of complexity sustained by energy flow. Even today, the echoes of protocells remain within us. Every living cell preserves the same logic of boundaries, gradients, and cycles that defined the first protocells. Lipid membranes still separate the inside from the outside. Ion gradients still drive metabolism. Autocatalytic networks still define the cell's identity. The modern cell is a highly evolved descendant of those ancient chemical compartments, carrying forward the same thermodynamic imperative: to maintain structure by consuming energy and exporting entropy. In this sense, life never escaped its origins. It refined them. The philosophical implications are equally deep. The protocell marks the moment when the universe began to recognize itself, when chemistry developed the capacity for self-reference. A protocell maintains its boundary by processes that depend on the boundary itself. It exists only by preserving its own conditions for existence. This circular causality, known as autopoiesis, defines all living systems. The origin of life, therefore, was not a singular event, but the emergence of a self-sustaining logic, a loop of cause and effect that allowed matter to persist, adapt, and evolve. From that humble beginning, evolution took over. Natural selection refined protocells into true cells, cells into communities, and communities into organisms. The boundary that began as a fragile film of fatty acids became the fortress of DNA-based life. Within it, information and metabolism coalesced into a single purpose: continuity. Every living thing today, from microbe to human, is a descendant of those first vesicles that learned to couple chemistry and survival. In their simple physics lay the seed of consciousness. For once, matter began to preserve its pattern through time. Awareness had a foothold in the universe. Thus, the emergence of protocells and molecular selection was the final act in life's chemical genesis. The planet's elements, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, gathered into structures capable of maintaining themselves against chaos. Through boundary and flow, through selection and feedback, the Earth's chemistry became aware of itself. The protocell was not the end of prebiotic evolution, but its culmination. The moment when matter first drew a circle around itself and said, in the only language it knew, I am.